All righty, it is all yours, Dave. Hey, Dave, we cannot hear you.
Is that better?
There we go.
Okay.
Yep, perfect.
All right. Good morning, everybody. I'm Dave Perskevich. I'm one of the customer assurance people here at Behler-Young. I'll be running the training today. This is basic heating, part one. So the intent of today is introduction to heating, combustion, fuels, the basic components of a gas burner, combustion analysis, basic idea what that is. So that's what we're going to get into here. Like I like to point out, there is 4 of us on the customer assurance team here, not just one. So all 4 people are available to you. So if you're looking for help, and like today, if you try to call my number, obviously I'm teaching, so you won't be able to get hold of me, but you can reach out to the other 3. We got Larry Mullins, Mike Gerlich, and Carrick Steffens. So all 4 of us are available to you. So, again, if you're trying to get a hold of one of us and we're not available, don't stop there. You can always reach out to the other 3. Even, if you're calling from the west side of the state, you can call us on the east side, or if you're on the east side, you can call Larry on the west side. It doesn't really matter. We're all 4 here to help you. So you want to click on that there. All right. All right, there we go. All right, so on a Zoom meeting like this is a little bit different than live training if you haven't been to one before. So over on the bottom of the screen there, you'll see there's looks like a microphone button. There should be a red line through it that's showing you that your microphone is muted. I'm going to ask you to keep your mic muted the entire time, because if the mics get turned on, we get a lot of feedback and it gets really kind of confusing. In the center of the screen there, you'll see, it looks like a little chat window, like a little thought bubble from a cartoon. If you click on that, that will allow you to ask a question, and you're going to direct the question to Behler-Young, which will send it to Isaac, and then he can give me the question when I stop talking for a second, and then we can ask it then. Or we're going to take a break at about 10 o'clock rather, and then of course at the end at about 10:30 or so, or I'm sorry, 11:30. And if you want, I'm going to open up a question session there, that if you want to open your microphones at that time, you can ask your questions. But other than those 2 times, I'm going to ask that you keep your mics muted the rest of the time. So that being said, we're going to get started. So first thing we have to talk about is safety. Again, this is a basic class. So I imagine most of you haven't had a whole lot of exposure to heating. So we got to start off talking about safety. All right. Electricity is one of the big things that we work with. So all of our furnaces, our air conditioners, everything is using electricity. So again, being new to working with it, we need to be very careful how we handle it. Electricity is not a scary thing as long as we're careful how we deal with it. So before we work on anything, we need to shut the power off. All right. We want to confirm the power's off. So just because the switch or the breaker's off, we don't want to assume that power's off. You know what assume is. So we want to use a meter. We want to test what we're working on to confirm that it is dead or the power's off. We want to lock it out. So there's little breaker locks or marking the breaker to make sure nobody's going to turn it back on. Now, occasionally we're going to troubleshoot things that are live. All right, meaning the power has to be on. We're trying to do some controls testing. So we want to use extreme caution when we're messing with live power. A lot of the stuff we're going to deal with is low voltage that we'll talk about, but there is some parts that are high voltage. So again, we want to use caution when we're working with live equipment, so we don't get ourselves. It's not just getting electrical shock, but it's actually arc burns, they call them, because when you have a short electricity, it creates a lot of heat. extreme amount of heat. So it's, again, it's electrocution, shock, and electrical burns. So we got to watch out for it. And I did have electrical burn on my hand once. It's not a pleasant thing. So again, just be careful. Gas. When we're dealing with gas, be it propane, be it natural, which are the two main that we're going to deal with, we can have gas leaks. All right, we have gas leaks, and we can accumulate gas in a space, and we can cause an explosion, ignition. Turning a light on when there's a lot of gas in a room can be enough to ignite it. So that's something else we want to be careful of. Working with gas, they're both flammable in the right amounts, as we're going to talk about. So we want to use appropriate leak testing means. I've seen guys try to use their lighter to find a leak. That's obviously not the best way to find a leak. Using soap bubbles or appropriate gas detectors. If we have a large amount of gas in an area and you smell it, and we want to avoid the open flames, avoid turning lights on. You want to open the windows, you want to ventilate the area. Again, avoid any type of spark. All right, so when we do have a high concentration of gas in a space, we want to ventilate. All right, before we do anything else, before we make any type of spark, turn anything on, we want to ventilate the area, all right, to get rid of that accumulation of gas. And you're going to see in a minute as we get going, you can actually have too much gas in the area to ignite. But as you ventilate like this, you're going to lower that quantity of gas, and we can get to a point where it can ignite. So, all right, appropriate safety gear. All right, we're going to be working with power tools, with extreme heat, extreme cold, sheet metal, which is very sharp. So gloves are a good thing. Eye protection. We got pieces of stuff flying when we're working on duct work. Or of course, appropriate shoes. We shouldn't be wearing flip-flops on a job site. All right, when you want appropriate shoes, that are going to be safe for walking around while we're walking around. No tennis shoes, no flip-flops. Hearing protection when we're working with, especially some of the loud power tools. We want wear hearing protection. And the one I always like to add, and this is near and dear to my heart, is knee pads. I'm assuming most of you guys are new to the field, and it was told to me when I first started years ago, wear the knee pads so you don't get arthritis. And that is a great piece of advice. And I strongly advise it, because here I am at 57. And when I walk up the steps, my knees make a crunching sound because I didn't wear the knee pads. So we do spend a lot of our time on our knees. And so one of the things you should do is invest in a good set of knee pads and wear them. And your 57-year-old version of you will be glad you did. Okay. So basic heating, this is an introductory training intended to introduce new technicians to basic combustion, the upper and low, I gotta do a spell checks. Upper and lower explosive limits, fuel properties, combustion and dilution air, burners, manifolds and components, gas pressure regulation and measuring with inches water column, BTUs, what does it mean? History of heating equipment, chimney effect, draft natural assisted, draft inducer, heat exchanger, basic furnace components, basic furnace controls, and basic furnace operations. So that's the stuff we're going to dive into here today. So hopefully that's what you were expecting. Okay, so we're going to start with combustion. Combustion is a chemistry. In chemistry, we call this a type of reaction that produces fire, a combustion reaction. Combustion is a high temperature exothermic redox chemical reaction between a fuel and oxidant, usually atmospheric oxygen, that produces oxidized, often gaseous products in a mixture termed as smoke. So long story short, we burn something, we generate heat. It is a chemical reaction, and we have an exhaust. We have a byproduct. So in the depiction here, you see everybody sitting around a campfire, right? There's a chemical reaction creating a fire. We're converting the fuel in the wood to heat and light, and we're also generating smoke. So that would be the gaseous byproducts. All right, so anytime we have combustion, we have a gaseous byproduct that we have to deal with. All right, what you're going to find as we get into this, you're going to see that yellow in that flame means there's a lot of carbon coming off of this. All right, so we're going to talk about types of flames and things like that. So anyway, so flame is or combustion is a chemical reaction. Now, we need three things for combustion. You take away any of the three of these and we don't have combustion, all right? We need fuel, obviously. We need something that will burn. We need oxygen, okay? So we need oxygen in a proper amount, and we need heat. Now, pure oxygen makes almost everything flammable. So, but oxygen itself is technically not flammable. It makes everything else flammable. So this is the combustion triangle. We have to have all three things in the proper amounts to have combustion. I take any of the three away, combustion goes out. There was an old movie that John Wayne was in. It was Hellfighters, I think it was called. And they were putting out oil rig fires. They had these rolling oil rig fires and they would use explosives. And basically what would happen is as they put these explosives around it, it would remove all the oxygen from the fire, as the explosive would snuff the fire out by removing the oxygen. So removing any one of these three parts and the combustion will go out. Okay, so combustion is three parts. We need fuel, the correct amount of fuel, okay? Because not enough fuel, it's not going to burn. Too much fuel, it's not going to burn. Now, the danger with too much fuel is as we start to ventilate, we're going to drop that percentage of fuel to the point where it is combustible. So air in the correct amount, enough, but not too much. All right, the correct amount of oxidizer, oxygen. Okay, oxygen comes out of the air. So 21% of our atmosphere is oxygen. That's where the air comes from. So we need the right amount of air or oxygen, but not too much. Because again, too much oxygen or air, we don't have enough fuel. So it's in the right combination. So enough, but not too much. Not enough air and it won't ignite either. It's going to suffocate. And then we need a heat or ignition source. So every fuel has an ignition point. So we need heat to that point to start the ignition. Could be a flame. We could be a spark. Could be compression, you know, like a diesel engine, they use a compression to start the ignition. But either way, we need a source of ignition or a source of heat. So those are the three things required for combustion. And we'll dive into those a little further in a minute. Fossil fuels, all right. Currently, and again, down the road, this could change. We are still working with primarily fossil fuels. Fossil fuels were byproducts. I know we always toss around the joke of dead dinosaurs, but basically what it is dinosaurs and plants from, you know, millions of years ago that deteriorated and over time, during decay, they became a fossil fuel. Fossil fuels, we use coal. Coal is still some used, still very inexpensive, obviously very dirty there. So we're using less and less, mostly in power plants. Natural gas is a natural occurring gas by its, like its name. Liquid propane is a byproduct from crude oil. And then of course, fuel oil, which is also crude oil based, but they're all fossil fuels. They're all carbon based that were created from the decaying plants and animals. So with carbon-based fuels or fossil fuels, we want to heed this warning here. Incomplete combustion while burning fossil fuels can produce deadly carbon monoxide and even displace oxygen, causing suffocation. So this is a concern when any of the fuels that we're dealing with. Number one is incomplete combustion carbon monoxide, which is deadly. We'll talk about that a little bit more. And then we can also displace the oxygen because the fire uses the oxygen. So if we use up all the oxygen, then if you walk in, obviously you can suffocate. So this is a big warning. We'll talk about a little bit more as we go when we're dealing with combustion. So we have upper and lower burn limits. Okay, so the point at which we have enough fuel to start burning, and then the point where we have too much fuel and it won't burn. So fuel requires a proper mixture to burn or explode. Okay, so the upper explosive level and the lower explosive level. So the upper is if I have more than this, it won't ignite, and lower is if I have less than this, it won't ignite. So here it says natural gas has a lower explosive level of 5%. So picture a room, whatever room you're in. If you have some natural gas leaking into that room, right? You can smell it. And you had some type of meter to read that, and you are at 3%. All right, there's 3% natural gas in the room you're in. It won't ignite. All right, it's below the lower explosive level limit. So as the leak continues and we get to that 5% in the air, so again, 5% of the air in the room you're in is natural gas, and you hit a light switch that sparks and we can ignite it, right? It can burn. Now, if we continue to add gas to that room, and let's say the amount of gas in the room you're in gets up beyond 15%. So now there's 15 or 18, 20% natural gas in the room you're in. Now it won't ignite anymore, right? Because now it's too much fuel. That's a real dangerous one though, because what happens? It's at 20% fuel, right? You open the door, that fuel starts to leak out, that percentage starts to drop, we get down below 15%, and now we're explosive. Okay, so that's the upper and lower explosive limits, and we're going to talk about that with the different fuels we work with. But the upper is much more dangerous than the lower, because again, if we're beyond the explosive limit, when we open the window, we start to ventilate, and that percentage starts to drop. We fall below the upper explosive limit, and we've now have an explosive atmosphere. So, all right, too little fuel, too much oxygen. So if I don't have enough, I'm below the lower limit. It won't burn because I don't have enough fuel. Too much fuel, again, I've got more fuel than above its upper explosive limit, and it won't ignite. Again, it is the most dangerous because as we ventilate, that percentage comes down and we can get below that limit. Okay, no ignition. So I can have perfect amount of air, perfect amount of fuel, and if I don't have a heat source, the proper heat source to ignite it, I can't ignite it. And I say proper heat source because different fuels have a different ignition point as far as temperature. So we need the right amount of heat or ignition for that particular fuel. So upper and lower burn limits of a fuel. So fuel utilities often refer to lower explosive level when classifying safety of a fuel leak. All right, so they use percentage of the lower explosive level. The closer to the percentage is to 100%, the more imminent to danger. So on natural gas, that limit is 5%. So the closer we get to that 5%, the more imminent to danger. So the utilities rate the severity of a leak by that. Okay, upper explosive level concerns, fuel concentrations that are higher than the upper explosive limit are considered to be non-explosive. Again, above, there's too much fuel to burn. They can become explosive when we ventilate, we open the windows, start to let some air in. We add more air, let some gas out. We lower the concentration, and then we get below the upper explosive limit and cause a decrease in fuel concentration that can cause fuel mixture to enter the explosive range. Okay, so when we have or beyond the upper explosive level, as we ventilate, we are going to fall into the explosive level before we get down below the lower limits. Okay. This is for example purpose only. So I'm going to ask you not to do this. I'm just using this as an example because gasoline we can all relate to. Now, right here is a bucket full of gasoline. Okay, gasoline is extremely flammable. We're going to do some comparisons with gasoline. However, the liquid itself, that's pure gasoline. Liquid gasoline will not burn. It has to be vaporized. All right, so now that circle I have here, that indicates the vapor coming off, right? So if I get far enough away from this bucket, the concentration of gasoline vapor is very small, it won't ignite. As I get into the circle, now I am to a point where I have a high enough concentration of vapor that a match will ignite it. Okay, so within the circle, it will ignite. Now, if I move down to the liquid, if I could actually get a match into that liquid without the vapor being there, it's not going to light. Okay, because it's above its explosive limit, its upper limit. Okay, it's liquid. I don't have any oxygen, so it won't ignite. It's not until that I vaporize, like in the circle here, where I'm in that limit. I'm above my minimum, but I'm below my maximum. that it will ignite, because I have both the right amount of oxygen and the right amount of fuel, and any source of ignition is going to light it off. Okay, so this little chart here, we're going to refer to a few times today. So we already talked about natural gas. Now, natural gas is the safer of the two gases we work with. It's not readily available to a lot of outlying areas that don't have a pipeline, so we end up with propane. So if I look at natural gas there, this column over here, second from the right, it says lower explosive limit of gas in percentage. So natural gas is 5%. We already talked about that. So less than that, it can't burn. The upper explosive limit is 15%. Above that, it can't burn. So the sweet spot is between 5% and 15%. Doesn't mean it's going to burn good. It just means it's going to burn. Okay, so propane. Now propane, look, it has a lower explosive of only 2.2%. So I need less propane in a space to make it explosive. And the upper limit, though, is 9.5%. So it is also less. But again, like we talked earlier, once we fall below that limit, as we ventilate, we're going to be back in the explosive area. Butane, I'm going to throw out there because we do use that as a refrigerant actually in some places. So we want to take a look at that. So butane would like what you have in your lighter. The LEL, or lower explosive limit of butane, is only 1.9. Okay, so doesn't make a great heating fuel because we're starting to get to a very dangerous point with it. And its upper explosive limit is 8.5%. Now let's take a look at gasoline, because that was our example. Look at gasoline. We're all the way down to 1.4%. So there's not a whole lot. We don't need a whole lot of gasoline vapor to be explosive. And then 7.6 is the upper explosive limit. Anything above that, we have too much. But again, we've talked about once we ventilate, we fall below that level, it becomes explosive. Okay, so that's our fuel. Again, we're going to talk about it a little bit more in depth in a minute. So now we need oxygen. Where's the oxygen come from? If you go by the hospital, you'll see the big white tank. It says liquid oxygen and it says flammable. Like we said, it's really not. It makes everything else flammable. So, but where do we get the oxygen for combustion? Well, the air we're breathing, hopefully, hopefully it's clean air, contains roughly 21% oxygen, 78% nitrogen, and a little bit of some other stuff. Okay, hopefully that's the mixture you're breathing. So that's where our oxygen is coming from. It's coming from the air. Now, we can burn up that oxygen, right? Because the gas, as it burns, it's using the oxygen. So that's coming from the room. So we can use up the oxygen and lower that level. So that's, again, one of the things we got to be careful of. So oxygen is one of the 3 parts required to start combustion. We get this from the air we breathe. Nitrogen in the air doesn't play a part in combustion. All right. It is possible to use up all the oxygen in the air if we are in a sealed space, no new air being produced. So you take a candle, for instance, you probably did this as an experiment in junior high. You got a candle lit, you put a glass over the top of it, and in a few minutes, the candle goes out. All right, because what happened is the candle used up all the oxygen. So we took away one of our 3 parts of our triangle, the fire goes out. Okay, so let's talk about flammable limits again for natural gas. So the upper limit is 5%, or the lower limit is 5%, the upper limit is 15%. So the flammability range is between 5 and 15%. So again, the depiction of 100%. So this would be in a room. So the room you're in, the circle is the air. So if I'm below 5%, I'm not explosive. If I've increased the amount of gas in there up to 15%, I am explosive in that area. When I go beyond above that again, I'm no longer explosive. All right, so between that 5 and 15%, we will achieve combustion. Again, not good combustion, but we'll achieve it. Outside of that, we won't. Okay. So we're going to take a look at natural or LP. So liquid petroleum, or LP. If you live in an outlying area, you might have a tank like this in your yard. Okay, this is LP, liquid petroleum. It is a byproduct of production of gasoline from crude oil. So that's thus its name, liquid petroleum. In this tank, it is in a liquid state. All right, they only fill this tank to 80% because we've got to leave room for expansion. So believe it or not, the liquid actually boils off and vaporizes. So the top of the tank is filled with vapor, which is what we're going to use. We're going to draw the vapor off because liquid propane directly is not going to burn. We need to vaporize it first, mix it with oxygen. So we're going to draw the vapor off the tank, send that into the house. So lower explosive limit of LP or propane is 2%. The upper limit is 10%. So between 10%, 2% and 10% in the space, all right, like this red area is where it's going to ignite. All right, below that or above that, it won't ignite. So if we're at 20% propane in the space, it won't ignite. But again, as we ventilate, we're going to drop that percentage. So hopefully this is all making sense. So again, there's a range in where that fuel will burn. And again, when I say it's going to burn, it doesn't mean it's going to burn good. At 5%, it might not burn so great. Okay, at 10%, it might not burn so great. It's not going to burn cleanly, but it will burn. Okay, butane. Again, I bring up butane because we can kind of relate to it because we do have, you think of a cigarette lighter uses butane. We're starting to use, believe it or not, butane as a refrigerant, some small refrigerators, very small refrigerators. But butane is getting a little more dangerous to use because the lower explosive limits are a little bit lower. So if we look at that, the lower explosive limit is only 1.5%. The upper is 8.5%. So the flammability range is between 1.5 and 8.5%. So again, the picture is the air in the room. Under 1.5%, nothing, it won't ignite. 1.5 to 8.5, it will ignite. Above that, again, it won't ignite. All right, so it will burn only in that red area. That's when we have the proper amount of air, fuel to achieve combustion. All right, so that's the lower and upper flammability limits. Now, those are important to know, not just for heating, but as we go into the new refrigerants that are coming down the road. I'm assuming, again, most of you are fairly new to this industry, but the refrigerant we're currently using, R410A, will be going away, and the new refrigerant is going to be what we call slightly flammable. So that lower and upper explosive limits will come into play when we start learning about that. So again, it's an important thing to understand. Okay, so perfect combustion. What is it they like to say? We don't live in a perfect world, right? We like to think it is. I think mine's pretty perfect, but we don't live in a perfect world. All right, so perfect combustion is basically no byproducts. We've burned off all the carbon. The only thing we have left is a little CO2, a little oxygen, and heat, and some moisture. All right, we got some water. So if we have a perfect mixture, so when the fuel to air ratio is exactly perfect, would result in perfect combustion, which again, in the real world is almost possible to achieve. We're just going to try to get close. So there's too many variables. So with perfect combustion, all the fuel that we're putting into the burner and the mixes with the oxygen, and it all gets used up. Okay, so there's no leftover fuel. The carbon's all gone. So the only byproducts in our exhaust, remember the smoke coming from the fire we talked about? We'll call that products of combustion. All right, because we really don't have smoke off of natural gas, but we do have a vent, products of combustion. All right, so the only byproduct or exhaust or products of combustion would be carbon dioxide, CO2, which we exhale. Some of us who talk a lot exhale more of it than the rest of us. I'm pointing at myself. CO2 is the bubbles in our beer. All right, so it's safe. It's not harmful to us. Trees like it. H2O, of course, water and heat. All right, nothing else. Okay, no carbon monoxide, no aldehydes, no other byproducts. Under perfect combustion, we have no unsafe byproducts. Everything has been burnt completely. Okay, so we can only hope for what we call complete combustion. All right, so we are going to have some, we could have a little, other things in there. We didn't burn it all off because, again, we can't have perfect combustion in a non-perfect world. All right, there's just too many variables. So we're hoping to achieve complete combustion. All right, so this is where we're burning off all the bad stuff. All right, so when we have complete combustion, all the fuel and only some of the oxygen remains. Okay, this is what we hope for in the real world. Now we can measure the leftover oxygen to determine how our combustion was. Okay, the only byproduct or for the products of combustion would be carbon dioxide, again, that's safe, water, H2O, oxygen, nitrogen, so there's some nitrogen left, and heat. Okay, again, there's no carbon monoxide, still clean. All right, you see the little flame over my head, the little blue flame is blue. Blue is good. Remember that campfire was all yellow? That's all burnt, unburned carbon. This blue flame is good. You always hear people talk in our industry. Did you check the burner flame? Yes. Is it blue? Okay, it's good. That's how we used to adjust flame. We were taught to adjust the air till we got blue. All right, so that indicates complete or thorough combustion. So incomplete combustion. Now, if you look at this flame over my head, this is a burner on a stove, and you can see that nice blue flame off to the off above my left shoulder, or rather my right shoulder, it's blue. There's no yellow in it. That's complete combustion. That's clean combustion. There's little orange tips that can be dust and other things in the air. But here, you can see the yellow flame. All right, the yellow lazy flame, okay? That's where the carbon monoxide is coming from. So what we see there, the blue, that's good. What we see here is not good. When we got that yellow, we have incomplete combustion. There's carbon still coming off that flame. There's a bunch of byproducts that are coming off of there that we're not burning off, which are dangerous. So not enough oxygen. All right, there's the key. If I don't have enough oxygen, I get incomplete combustion. All right, what if I have too much fuel? Well, that's the same as having not enough oxygen, right? So if I'm at my upper explosive limit, it'll burn, but not good. Well, if I'm at the upper explosive limit, so if natural gas is 15%, that means I don't have enough oxygen. So I don't get complete combustion. So the byproducts or exhaust would contain carbon dioxide, again, CO2, water, H2O, oxygen, nitrogen, heat. And in the byproducts, we can also have unburned fuel and carbon monoxide. Okay. Now, carbon monoxide, I'm sure you've heard of. There's always news stories on it. That's the thing that's poisonous, and it has no scent. And carbon monoxide in a house can actually put you to sleep and kill you in very small quantities. So incomplete combustion gives us off carbon monoxide. Now, carbon monoxide has no scent. Now, if there's any of you newbies out there who've been on a furnace that's sooted, you're going, oh, I could smell it. No, you couldn't. There are some other gases in the carbon monoxide that you're going to smell. All right, so carbon itself. So this black sooty stuff, imagine powdered sugar that's black. All right, throw it up in here. That's what the soot looks like off of a furnace that has not been burning properly. And it's just as messy as what I just described to try to clean it up. Okay, so incomplete combustion, we still get the CO2, the water, nitrogen, heat, but we also get carbon monoxide and some other burned up byproducts, such as soot or carbon. All right, if you look at this picture over my head, this is the 90% furnace exhaust, and you can see the black sooty stuff on it. This thing was not burning clean. All right, so it was producing carbon monoxide. Okay, so carbon monoxide is odorless. Now there's something called aldehydes. All right, why do I remember that? I don't know. But aldehydes are the thing we smell. It's kind of a sweet smell. Oh yeah, they smell. And when you smell them, you're gonna, oh, that's what he was talking about. That's not the carbon monoxide. It just goes with the carbon monoxide. Okay, that you smell that. However, if it's leaking into the house, you don't smell it. It's completely invisible. And it can only be detected by meter or parrots. They used to do this with parrots in the mines. They put the parrots in the mine, and if a parrot dropped dead, they know there was too much gas in there. You know, that's probably not a good way to do it anymore. So we use meters for detecting it. Okay, and if we get above the limits of carbon monoxide, things can happen. So the meter up here on the top, the yellow one would be like a handheld that we'd use, the fire department might use when they come out to the house. Okay, this here is one that would be mounted on a wall in a house. You probably have one at your house, might not have a display on it, but at a certain level, it goes off. All right. So fuel properties. What the heck did I do? I got a chart here about our quantities of CO. I think I might have moved it. Anyways, CO in over 50 parts per million. 50 parts per million. So that's 50 millionths. I think that would be right. Is already at the dangerous threshold. So it's not much. Okay. So we can withstand 50 parts per million or less for like 8 hours. And then when we get up around 200, death is imminent in a couple hours. So it's stuff not to mess with, but it's not to be afraid of. Okay. So fuel properties. So different fuels have different properties. So fuels are selected for use in heating appliances based on their properties, right? Why did we select certain fuels? Availability. Well, we have a huge abundance of natural gas in the country. It's fairly inexpensive. We can pipe it to, urban areas, some outlying rural areas. So it's relatively easy to get places and it's abundant. Cost. It's not very expensive. So it's a good fuel. What about propane? Well, we can't get natural gas everywhere. So propane is in liquid form, so it's better suited to put in a bottle or a tank, right? Okay, so propane's a good choice for that. So out in our outlying areas where we don't have natural gas piped in, because natural gas is a gas, it's not a liquid, it's in a gas form, so we can't store large quantities of it in your backyard. Where propane as a liquid, we can. Propane's fairly inexpensive. Now, those of you on propane are yelling at me, saying not anymore, because it's gone up quite a bit. And it follows the price of gasoline because it is a byproduct. Okay. Let's talk about gasoline. Gasoline would not be a good safe fuel in a house because it's very volatile. You're going to find out in a minute. We're going to look at it, some more properties of fuels. Another reason why gasoline wouldn't be a good choice because it's just so volatile. It's very dangerous to handle for some other reasons than the low explosive limits we already looked at. Very climatic conditions. Fuel oil. Now, some of you may use fuel oil. Fuel oil is a real safe fuel because you can throw a match right in a bucket of fuel oil and it's going to go out. You got to heat the oil first. So the problem with fuel oil is as it gets cold, it starts to get thick. Okay. Some fuel oils in really cold climates you can't use without heating it. All right. Propane, because propane below 50 below zero will not vaporize anymore. Okay, so if you're in a super cold, well, if you're living in a place that's 50 below zero, you probably should move. But if you're living in that place, propane might not vaporize. So it might not work in those locations. So the climate we're using it in is also a consideration. Safety. Can we safely distribute it? All right. Can I move fuel oil? Sure. The guy comes out, he puts that nozzle in your little fill tube, going to the tank at your basement, no problem. The propane guy comes out, hooks up your propane tank behind the barn, fills it up. Natural gas is piped right to the house. Okay. So again, this is a fuel oil fill. Guy's wearing a pair of gloves just to keep the stinky oil off his hands. That little nozzle there that he's putting it into goes into the tank in the basement. All right. If we use gasoline or jet fuel, you'd be wearing a fire suit, right? So obviously something we'd need to wear a fire suit with, we don't want to use. It's not a safe fuel. Okay. Natural gas, again, the guy, we just pipe it. All right. We have to be careful because it's explosive, but we don't need a fireproof suit around it like we might use with rocket fuel. All right. So the next thing we want to look at is something called specific gravity. All right. Now, we're not getting into chemistry here, but some of this has some relevance to what we do and understanding handling of fuels. So specific gravity is the ratio of a density, mass of a unit volume of a substance to the density of a given reference material. What the heck does that say? So we take one thing and we compare it to everything else. So basically what we do, we give air a baseline specific gravity of 1. So air has a specific gravity of 1. And we're going to compare these gases to air. So if it's less than air, it will be less than 1. If it's heavier than air, it'll be more than 1. So air is the baseline, specific gravity of 1. Some gaseous fuels are heavier than air, while others are lighter. So you're going to see some are heavier, some are lighter. The lighter ones are a little safer. The heavier ones are a little more dangerous. Okay, so fuels that are heavier can cause serious health issues as they displace oxygen. They do something that is called puddling. And we're going to look at that in a minute too. So in order to determine if the fuel is heavier or lighter than air, we need to look, compare it to air, all right, to see if it's lighter. So we're going to go back to this chart. And the first one we're going to look at is natural gas. Now, if I look at the third column, it says specific gravity, air equals 1. So compared to air, so 0.65. So is natural gas lighter or heavier than air? You should all be yelling out, heavy, lighter, lighter. I amuse myself, you gotta understand that. So anyways, so 0.65, so it's lighter than natural gas. All right. So what does that mean? Well, this is actually fog coming off a lake, but the natural gas being lighter than air, it will rise and dissipate, right? It will rise out of the house. It'll rise from wherever and dissipate in the atmosphere. Okay. Because it's lighter, so the air will stay down, the fuel will rise and dissipate. It'll go up the chimney, go out the windows, it dissipates. Okay. Now, let's take a look at propane. Propane is 1.56. So it's heavier than air. Okay, butane, 2.01. It is heavier than air, twice the weight of air. And then gasoline, look at that, 3 to 4 times heavier than air. So again, why gasoline is so volatile. So what these 3 fuels will do, if there's a leak, is they're going to sink to the floor, right? So imagine, picture, you got your Italian dressing bottle in the fridge, right? And the water or the vinegar and the oil separate, right? The oil goes and sits on the top because it's lighter. So it's going to rise to the top. Okay, so the same thing's going to happen here. Is that these are heavier, so they're going to sink to the bottom. So if you were to look in a basement, again, this is fog, but this is a good depiction. So imagine you're in a basement. Imagine this little valley is the basement of a house, and you have a leak, a propane leak. And that propane is heavier than air, so it's going to settle to the floor, and it's going to do what we call puddle. So we're going to accumulate this propane down at the floor, or gasoline down at the floor. So if we're accumulating it down at the floor, we can get above that explosive limit, the lower explosive limit. All right. We can also displace oxygen. When we get so much gas accumulated on the floor, we can also displace oxygen. Okay, so again, why the specific gravity is such a big deal on a fuel. So propane's not real bad, but gasoline is 4 times heavier than air. So every so often you'll hear somebody in their basement cleaning car parts with gasoline, and the water heater ignited it because that gasoline vapor pools at the floor till we get enough of it, and boom. Okay, so when dealing with propane, we need to be a little more cautious because it does puddle. It's heavier than air. It'll sink to the floor and start to accumulate. And we can more easily get to that explosive limit. Natural gas is lighter, so it's going to dissipate. It's not going to puddle. It's going to dissipate throughout the house and outside. So it's a little safer to deal with as far as this goes. But this is something we need to know when we're dealing with it. All right, so ventilate. When we exceed that threshold, if we have gas in the area, we've detected gas, be it below the explosive limit, above the explosive limit, we need to ventilate. We need to ventilate. And if we're above the explosive limit, we don't want to ventilate with electric fans, right? Because if we have too much, we're above the explosive limit. When we start letting air in like this, we're going to drop it below the explosive limit, and the motor in a fan, the switch on a light could ignite it. So again, something to be careful of. Not to be afraid of, just need to understand, right? We need to know how to handle it. All right, so we're going to get into, so that's our fuels. Now we're going to get into the burners. Now I have my fuel, natural gas, propane. Now I have to put it in the furnace, right? We need to make usable combustion out of this thing. And we need to control combustion. So we're going to take a look at what we need to do to put it in the furnace here. So we can see I got burner above, I got a manifold over there, I got some orifices, I got some in-shot burners behind me. So we're going to dive into some of these. So up at the top of the old ribbon style burners, on the far right over there was something that's similar to something they used to call a barber burner. Back in the day, remember we used to heat with coal? And a lot of coal furnaces were converted with a burner like that. Okay. Down here is a modern in-shot burner. Okay. They all basically work the same way. If we go to that little barber burner over there, that wedding or birthday cake looking thing, each one of those little brass burners has the same stuff that this diagram has over my head, same parts that each one of these burners have. Oh, all right. We have a primary air intake. All right. We have a place where they're going to mix. All right. And then we're going to have an outlet. Okay. So we're going to talk about these a little bit deeper as we go on. So the first thing I need to do is when I'm dealing with these burners is I need to control the rate gas is going into these burners. So I need to control the pressure. Okay. That propane tank might be 100, 200 pounds of pressure in the tank. So obviously I cannot put that in these burners. All right. So I have to control the pressure first. So gas comes in typically into a house. It's 7, 8 inches of water column. We'll talk about what that means. Some commercial businesses, you might have a couple of pounds coming in. The mains in the street might be, I'm sorry, much higher than that. Okay, so first thing we need to do is regulate the pressure. So that little circle thing in next to my gas meter is a pressure regulator. So we need to lower the gas pressure before it goes into the house, be it propane, be it LP. We're going to regulate it to a lower pressure. All right, so entering the building typically at a house is what's called 7 inches, 8 inches of water column. At the appliance, generally we're regulating it down to 3.5 inches of water column. Again, we'll get into what all that means. Commercial buildings, sometimes we can be a little bit higher coming into the building. But we're going to do the same thing with it. Now, propane, remember that propane tank out in your yard? Propane is in a liquid form, mostly in the tank, then it vaporizes, and then we let the vapor out. So if I go onto that tank, depending on how hot it is outside, I could have 100, 200 pounds of pressure on the tank. So the warmer it is outside, the higher that pressure is going to be. So I don't want to put 200 pounds of propane pressure to my furnace. So we have to drop it down. So if you look on the top of the tank there, you can see that little brown thing. You got the fill, and to the right, you got a valve, and then you got the little brown regulator. That's the primary or first stage regulator on the tank. So that's going to lower that pressure from 100, 200 pounds to about 8 to 10 pounds of pressure. And then it's going to transfer through a line like over my head here. See this little copper pipe? That's coming from the ground. That's going to the tank. And then it's going to go to a second stage regulator on the house, which is going to drop it down to roughly 11 inches, which is going to be our usable pressure for our appliance. All right, so this stage works the same whether we're doing natural or propane. However, propane is going to have two, generally one on the tank and one on the side of the house. All right, so you got the first stage regulator and the second stage regulator. Okay, so inches of water column. Have you ever heard the term before? And what's it mean? All right, if I had a glass tube and I filled it with water, and that tube was 27 3/4 inches tall, right? A column. There's 1 pound of pressure being applied by that 27 3/4 inches of water in that column. All right, so that's 27, almost 28 inches of water column. So if I take that 1 PSI, there's roughly 28 inches of water column in that 1 PSI. So 3.5 inches of water column is like, 3.5 28ths of a pound. Okay, so it's not very much. All right, when you sneeze, you're sneezing harder than that. I mean, gas pressure is relatively low, but that's what a water column is. Okay, so it's a measure, like I said, that 27, 28-inch water column produces 1 inch of pressure. So 27 inches is going to produce a little bit less, 26, 25, all the way down to 1 inch, which is going to be 1/28th of a pound, roughly. Okay, so it's not much pressure, but that's where this comes from. So how do we measure it? Well, these are YouTube manometers. We don't use a lot of these anymore because we have a lot of good electronics. These are still incredibly accurate. There are incline manometers. There's some different varieties based off of this, but this is where it all came from. All right, some guys still use these. Nothing wrong with it. Still very accurate. So if I look at the figure 1 there, you can see it's a U-shaped tube. All right, it's open at the top, and we fill it with water, and I can see the graduations. I've got 4, 3, 2, 1, 0, 1, 2, 3, 4, and then on the other side I have the same thing. Okay, those measurements are a 1/2 inch on each side, but those indicate 1 inch. So now if I go to the middle one here and I apply pressure to it, you can see the water goes down on one side, water goes up on the other side. So the water went down to 3, which those are 1/2 inch spaces. So it's 1.5 inches. I went up 3 with 1.5 inches. So that's 3 inches of water column. Now it's the graduations on the tube are marked at 3. So you don't have to do any math. It's simple. I'm pushing down enough pressure to push that water 3 inches. So it's 3 inches of water column. All right. Again, it's not much. You could almost sneeze that hard. Okay, so it's a 28th of a pound. Now, we're talking about gas pressure today, so we're going to use it for that. But other things we get into, we're going to talk about draft inducers. They create a vacuum. Ductwork. On my ductwork, you may have never even thought about this, but on my return air ductwork, there's actually a suction on there. We're sucking the air in. We can use this manometer here to measure the static in the ductwork, to measure the static in your vent system for your pressure switches. Okay, so we're going to use this same little device to do it. Okay, this is a YouTube manometer, fairly inexpensive, but hopefully it makes some sense of what we're measuring here. Okay, so again, this is water in a tube. We press water down, it pushes it down one way, pushes it up the other. That graduation is in inches. So 3 inches of water column. And then we can do the same thing with vacuum. We can pull a vacuum on it and it will do the same thing. We pull the water up on one side and the water comes down on the other side. And again, we have a 3 inch negative water column. Okay. Now, lots of different gauges, the YouTube manometer, which are still around, the old oil-filled manometer like you see over in the far left there. Magnehelic, some guys still use Magnehelic. It's just a gauge, but it's still in inches of water column. So it's still based off of this. Okay, Magnehelic were very accurate in their day. You can still get them. I know there's still some old timers like me that use them. This is one of the ones I caved in on though. I have one of these. Okay, we have digital nowadays. Okay, you guys are getting into this in a great time because we had incline manometers and YouTube manometers and Magnehelics. And nowadays you get this 1 meter, which does it all. So this does inches of water column, both vacuum and pressure. So I can set a gas regulator with this. I can test ductwork with this. All right, all in one little compact meter, which is incredibly accurate. And you don't have to worry about dealing with water in the middle of winter. Okay, so now we hopefully understand a little bit about what inches of water column is and how we measure gas pressure. So now we're going to dive into the gas pressure regulator, because we already talked a little bit about how we're feeding 3.5 inches of gas to a natural gas furnace, roughly 11 inches of propane to a propane furnace. How do we do this? Well, the gas meter over there, we all recognize, I hope. That big circle thing to the left of it is, is a regulator. Over my head here is a gas pressure regulator. Now, we can have one or two, or could be several in a house of these regulators. It's a fairly simple device. Okay, so if I look at this regulator right here, okay, just aluminum body, you can see that little blue cap there, that is a vent. In that little tower in the center is an adjustment screw and a spring. That's how we adjust it. Okay, now if I look over there, you can see the cutaway, and you can see the dome at the top, and right underneath it is a rubber diaphragm. Okay, so then from the rubber diaphragm down, you can see this little, what's called a tappet, or poppet rather. It's a little piston. So if you look on that one over there, you can see the little piston sticking down. It's attached to that diaphragm. So what happens is the natural gas is going to come in. It's going to go around that little piston, and it's going to go out. But what it's going to do is push up on that little this little poppet, this little piston is going to close, right? And it's going to stop flow in. So now the diaphragm is going to come back down, and it's going to open again. So the spring pressure is pushing it open, the gas pressure is pushing it closed. So the little poppet is going to kind of modulate, and the gas coming in could be whatever, and the gas coming out is whatever we set the spring tension at. So if it's set for 3.5 inches, it's 3.5 inches coming out. You know, so it might be 11 inches coming in. So again, as the gas comes in here, it goes past the poppet or piston. It goes to the outlet there. At the same time, it hits the bottom of the diaphragm, pushes against the spring, pushes this little piston or poppet closed to stop the flow. So the little poppet or piston modulates up and down between spring pressure and gas pressure to lower the gas pressure. So we have one pressure coming in, we have one other pressure coming out. Now, obviously, that little rubber diaphragm could fail. And what would happen if that little rubber diaphragm failed? Well, you're going to get natural gas or propane leaking through it. So if we look, this is another cutaway. You can see at the top of this, you'll see the vent orifice up over there, right next to the adjustment spring. You see the vent orifice. That's actually a vent. In the picture over there, that's where the blue cap is. So that vent is there for a couple of reasons. Number one is that diaphragm moves up and down. It needs to be able to move air too. So it'll push air out the vent, pull air back in, push air out. But if that little diaphragm ruptures, it's going to leak out there. All right. So that's the regulator. Now, springs can be different sizes for different pressure ranges. But again, this is just another look of a cutaway. You got your spring in the top pushing down on the diaphragm. Coming off the diaphragm is the little poppet. We have our gas inlet. Gas is going to go around the open poppet and out the outlet here. But at the same time, it's going to push up in the diaphragm against the spring, close the little poppet. The gas pressure is going to drop off. The diaphragm is going to come down again. So what's going to happen is it's going to do one of these, modulate to slowly meter gas in to lower it to the pressure we want. Okay, but again, that little vent there, in some cases, it will be going outside, all right, on bigger stuff. That can be a problem too, because if that vent gets plugged, that little diaphragm can't move anymore, right? So we may have a problem. On propane, you might get a little bit of ice buildup in that vent. Okay, that would stop this from working. Okay, this little chart here. So now we talked about gas pressure. Now, hopefully you guys can see this clear enough. It's a little fuzzy on this, but I think we can make it out. But anyways, all these little brass doohickeys here are called orifices, right? They have a specific size hole in them, all right, for metering the specific amount of gas, propane or natural, to the burner. All right, so we already talked about the pressure, because the first thing in how much gas we deliver is what our pressure is going to be. The second is what is our volume. So depending on the size hole in these orifices that are feeding the burners are going to dictate the capacity of each one of those burners. So if I look up at the top here, you'll see drill size 35. So if you go down that list, they're not in, most of them aren't in sizes like 3/8, 3/4, whatever. It's a number. So each one of those numbers, this is a drill size. Okay. And you can actually get a drill kit for these. If you ever needed to drill them out, typically we don't do too much of that anymore. You just buy new orifices. but you'll see there's 35, 38, 38, or 36, 37, 30, and so on, the different size orifices. Now, across, it'll say what it is in inches, decimal in inches. So that 35 is a 0.0995. In the blue across the top, it says inches of H2O, inches of water column, in case you didn't know what H2O was. So remember, we said natural gas normally runs at 3.5 inches of water column. So you see I have that circled up above. So a number 35 orifice with 3.5 inches of water column is going to produce 25,137,000 BTUs. Okay, that's how much natural gas we're going to burn. That's how much heat we're going to produce with that burner combination of this orifice at that gas pressure. Now, what happens if I increase the gas pressure to 4 inches? All right, well, look what happens. Now my output, I'm moving more gas through. All right, so a cubic foot of natural gas gives me so many BTUs. So the more gas I put in, the more BTUs I'm going to get. All right, the more heat output. So there you go again. So 26,872 at 4 inches. So it went up a little bit. Now propane is at a much higher pressure, right? We said it was 11 inches. Now look what this orifice will give us with propane. Over 69,000 BTUs. Now, generally, we're not going to have a single burner anymore that's that big. So for propane, we'd use a much smaller orifice. So if I went down the list there and I found another orifice at 11 inches that produced around the 25,000 that we had for natural gas, that would be the one we'd use. Okay, so generally, the orifice for propane is going to be much smaller than the orifice for natural gas. So we talk about converting natural gas to propane. We're changing orifices. We're generally changing the pressure regulator or pressure regulator setting because they work at different pressures. And you can see what would happen up there. If I took a natural gas furnace, I jacked it up to 11 inches of water column, and I put propane to it, I'm getting almost triple out of the burners. Now, the furnace isn't designed to handle it. It's not going to, remember, combustion's not going to be right. We're going to be sitting. So it's just not good. So hopefully that makes some sense. So the orifices for natural gas are larger than propane. And the pressure is lower. Okay. And it's just a difference of the capacities of the gases. And we'll see when we look at them a little bit further down the line here. We'll see some more examples of that. So the orifice sizes are very critical. All right, because that dictates the volume and the pressure, and that dictates the output of the burners. Okay, so again, hopefully this makes some sense. So if I were to try to convert this to propane, I would have to get the smaller orifices that produce, 20, well, if we look at 3.5 inches on natural gas, it's about 25,000 BTUs. So I'd have to find the appropriate orifice for propane that would produce the same amount of BTUs. That's how that sizing would be changed. Okay. Oop. So there's our gas. Okay. So actually I see it's 10:06 right now. So we'll get through this slide here. We're going to a slide or two, and then we're going to take a short little break. So, oh. Oh, there. Okay. So anyways, combustion air, we're going to talk about this for a second, and then we're going to take a 10-minute break. So combustion air. Now, remember, we needed the right amount of gas, which we just talked about, pressure, orifices, volume, pressures. And now we're going to talk about the right amount of air, because we need the right amount of air, because in perfect combustion, we need a perfect mixture, right? Or as perfect as we can get it. So we have primary air that's coming into the burners. There's the inlet, the air inlets in the burners. So that's coming into the burners, and it mixes with the gas inside the burners. So if you're thinking about a car, you think about the air going into the top of the carburetor. All right, before it mixes, and then it mixes with fuel inside the burner. Secondary is around the flames. So as the flame goes into the furnace, more air is going in around it. That's secondary air. Okay, that ensures complete combustion. All right, we're giving a lot of extra air to make sure we get good combustion. Excess air, that's leftover air. That means we had too much air, which is good, because too much air is okay. It just goes out the vent. Not enough air is not good. We get incomplete combustion. So we give a lot of excess air. That means we had enough for complete combustion. We had some leftover. And then we get dilution air. Okay, when we get into our gravity vent furnaces, and we're going to talk about the gravity venting here shortly, we dilute the air as it's going up the chimney, and it aids in venting. All right, it drops the temperature, it reduces the moisture, and it aids in venting, the dilution air. So we're going to talk about these 4 different airs. So if you look over my shoulder here on the picture, you can see combustion air right here is mixing before the burners. It goes into the burner, mixes with the gas, and then goes in. And then the secondary air goes in around the burners. The excess air is what's left, and then the dilution air goes into the chimney as the flue gases are venting. Oh, we're not clicking again. All right, so we're going to stop right here. We're going to take our break. It is 10:09 right now, so let's get back at 10:19. Isaac, are there any questions?
You are all set for now.
All right, so let's get back to it at 10:19, and we'll get started again.
Sounds good. Thanks, Dave.
All right, so can you hear me? I'm back on? Yeah.
Yes, yep, we can hear you.
All right. So, okay, so we're gonna get going again. All right, so welcome back. Hopefully you got a coffee or whatever you needed to do. Not many people smoke anymore on their breaks, but all right, so primary air. We're gonna talk about that first. Now, right behind me, these are modern in-shot burners, and you can see the little opening here where that red arrow is going in there. Okay, and you can actually see the light of the flame from inside that burner. Okay, so that's the primary air intake. All right. Now the gas is going to come in through the back of the burner. So if I look at the picture over there, you can see that little round circle. That's where the orifice would go. So that's where the gas would go. And then that opening there is the primary air intake. So the gas is coming in the base, air is going to come in around it. They're going to get into the venturi, see where it's kind of narrow here. And that's going to mix the two. So the primary air and the gas are going to mix, and then they're going to shoot into the burners. Now, almost all modern in-shot burners. Now, if you look at these, the burners themselves do not go into the tubes. They're shooting the flame in, but they're not going in. These are modern in-shot burners. Nowadays, I think pretty much everybody uses these. We may still have some old cast iron boilers and things that have the old ribbon burners, but primarily everybody's gone to these on this 80-90% furnaces. But they all work the same way. You got your primary air coming in at that shutter, and it mixes with the gas in the venturi. That's that little hourglass shape there. Now, some of the old burners, if you look at that picture over there that just popped up, you'll see they had air shutters. Okay, if we get into the old ribbon burners that went back into the furnace, or it's the old cast iron burners, and we adjusted that air shutter for our primary air. And back in the day, we did it by the blue flame. That's how I was taught to do it. You look down that burner and you turn that little deal there until the flame looked good and you locked it down. Nowadays, we do combustion tests, so we're a little bit more accurate, on our setting of these burners. Now, if that burner over there, if that shutter had gotten closed and I'd had it happen, or got full of dirt or lint, we didn't get complete combustion anymore. And then that's when we started sooting and carbon monoxide and so on. So again, most of modern furnaces, that's not adjustable, but there are still a lot of the old timers out there that you can adjust. Now, secondary air. So if I'm looking where that burner's going down that tube or the heat exchanger, there's more air being drawn in around it as it's shooting down that burner or down that tube. Okay, that's going to wrap around the flame. That's our secondary air. Okay, so that's adding a lot of extra air to make sure we have enough air for complete combustion. So that the primary air wasn't enough, we're going to add the secondary air down that tube there to ensure we have enough oxygen for complete or as complete a combustion as we can get. All right, so that's our secondary air. Okay, excess air is leftover air. So after combustion, the measure of excess air tells us it's one of the measures of complete combustion. Because if I've got a lot of leftover air, that means I had enough. All right, so that's part of the key. So the extra air ensures sufficient air available to cause complete combustion. All right, so we can measure that excess air. Okay, dilution air. Now, over my head here and that water heater over there, these are what were called gravity vent. Okay, so these furnaces or that water heater, they vented by gravity. Now we're going to talk about chimneys in a little bit, but if I look at that draft diverter, that's that little bell-shaped thing on the top of that water heater, you can see the guy's holding the match there. And the smoke's actually drawing up that chimney. That little draft diverter is actually open to the house. All right. So the flue gases are coming right out that pipe there, and it's drawing air from the basement, dilution air, to mix with the exhaust to aid in going up the chimney. So brought the temperature down of the flue gases, lowered the humidity, and aided in venting. All right. And I know that looks strange when you see that. You mean that's open right to the basement? That pipe right there sticking out the top of the water, that's where the flue gases are coming up. Yeah, because it's drawing basement air in. And like you see in the picture, if you took a match, it's one of the ways we check for a draft. You take a match, put it out where it's still smoking, and it should suck that smoke right up that draft diverter. Now, behind me here is an old furnace. And you can see at the top there where the cutaway is, it says exhaust. Okay, that's the outlet from the heat exchangers. So that's the 500-degree exhaust gas coming off products of combustion. And then you can see the front here where it says dilution air is open to it. So now it's drawing house air, it's mixing with the exhaust air, lowers the flue gas temperature. You can see it about 300 degrees, lowers humidity, and aids in venting. Now, if I blocked either one of these, what they're called draft diverters, I'm not going to vent. Okay, so we need this dilution air to aid in venting. Okay, over my shoulder here is a, over here, gas boiler. And you can see that has a bell draft diverter on the top, but it's the same exact thing. It's open to the space to allow for the dilution air to mix with the vent gas to go up the chimney. And if we didn't have that diverter, if that diverter got closed, we're not going to vent. Okay. So it's going to basically stop the venting from happening. So we needed to have that dilution air to aid in proper venting. All right. Okay, so now we're going to talk about how much of this air we need. All right, so this is a measurement, this is a concern, because if this is in a space and the space is fairly small, do we have enough air in that space to feed proper combustion, primary air, secondary air, dilution air, to keep that furnace running? Or are we going to use all that air up? You know, do we have enough air? Do I need to bring more air in? Okay, so again, this is all part of combustion. So cubic foot, 12 by 12 by 12. All right, is a cubic foot. So if I had a cube that was 12 inches by 12 inches by 12 inches, like on my little picture here, that is a cubic foot. Okay, so if you look at your gas meter outside your house, we pay for natural gas in cubic feet. So they charge us by the cubic foot of natural gas. All right, so for natural gas, 10 cubic feet of air is required for every 1 cubic foot of gas as primary air or as combustion air. So for 1 cubic foot of gas, I need 10 cubic feet of combustion air. I need another 50% for dilution air. Okay, that's the aid in venting. Okay, so a cubic foot of natural gas is 1,000 BTUs. All right. So for every cubic foot of natural gas, I get 1,000 BTUs. So if I have a 90,000 BTU furnace, 90,000 BTUs an hour, that would require, well, 90,000 divided by 1,000 be 90 cubic feet of gas an hour. So how much air do I need for that furnace? There's the question. So 90 times 10, because I need 10 cubic foot per of air per cubic foot of gas. So that's 900 cubic feet of combustion air. I need an additional 50% for dilution air. So let's look at this again. So 90,000 BTUs divided by 1,000 BTUs per cubic foot of gas is 90 cubic feet of gas. So 90 cubic feet of gas times 10 cubic feet of air is 900 cubic feet of combustion air. So 900 of those cubes. Then I got 90 times 50 because I need 50% of more of that for dilution air. So that's 90 times 50 is 450 cubic feet. So 900 cubic feet of combustion air, 450 cubic feet of dilution air, that's 1,350 cubic feet of air required for proper combustion for this furnace. The room this furnace is in requires at least 1,350 cubic feet of air every hour. Okay, so this is where this comes in. You know, we're in a tiny little room. So let's take a look at it, just kind of visualize here. So 1 cubic feet of gas requires 10 cubic feet of combustion air and 5 cubic feet of dilution air. So this just kind of give you an idea of volume. But in that particular furnace we just looked at, it's this times 90. Okay. And again, that's a cubic foot of air, 12 by 12 by 12. So just again, visualize the room you're in, you know, and if you're in a small 10 by 10 room, you're not going to probably have enough air in that room to run that furnace. Okay. So complete combustion, natural gas, 100 cubic feet of natural gas plus 1,000 cubic feet of air with 20% oxygen. Our byproducts will be water, nitrogen, carbon dioxide. Okay, if we get complete combustion. Again, the nitrogen is inert, the water is water, but we got to remember the water. And when we get into the higher efficiency furnaces, we have a lot of moisture. Look at that, 1.1 pound of water in this combustion. So so that water is a consideration. We have a lot of moisture to get rid of. So let's take this room. Let's say it's 10 by 10, 8 foot tall, right? So if I were to take the dimension of this room, and 10 by 10 by 8, that's 800 cubic feet of air in this room. So let's say this is a small mechanical room in a basement. And the basement's finished, right? So we close this mechanical room in, a washer and dryer is sitting in there, and a water heater sitting in there, and a furnace is sitting in there, and it's all nice and sealed up tight. Now, in our example there, a 90,000 BTU furnace needed 90 cubic feet of gas, which is 900 cubic feet of combustion air, which is 450 cubic feet of dilution air. So that's 1,350 cubic feet of air required per hour to operate that furnace. Now, there's only 800 cubic feet of air in this room. Okay, so we have to bring air in. We have to have vents someplace. We have to bring air in from outside. But again, this is a huge part of basic combustion. I have to have enough air to provide for that furnace right there. Okay, that furnace right there. Okay, so we 1,350 cubic feet of air is required. We need ventilation of some sort. Or what's going to happen if I try to run this furnace, I'm going to use up all the air in this room. Oh, and then I'm running out of combustion air. So now my flames start to get lazy. I start to create carbon monoxide. I don't have the dilution air I need. So now my chimney starts to back up into the room. I start dumping carbon monoxide into the house, into the space, and bad things happen. Okay, so again, this is a really important part of what we do of complete combustion, is having enough air for combustion. So knowing what that combustion air is an important thing. So I know you're just kind of diving into this, but this is important basic information to know for proper combustion. Because this happens in the real world, this happens. You get that sealed room, the homeowner builds, finishes the basement, makes a man cave down there, ties up that tiny little mechanical room. It's airtight, right? Because we don't want to hear that furnace and everything. And pretty soon, we got bad things happen. So, all right. So carbon monoxide can be a problem. You walk in that room, you're going to smell it. Not the carbon monoxide, the aldehydes. Okay, but we can cause a problem here. Okay, so now let's take a look at liquid petroleum, or LP. So LP is a little different gas than natural. As we know, it runs at a higher pressure. BTU content's higher. So 25 cubic feet of air is required for every 1 cubic foot of propane. So natural gas, it was 10 to 1. Here it's 25 to 1. Okay, so we need 2.5 times more air. Still need the 50% dilution air. So how do we figure this one? Well, 1 cubic foot of LP is 25,000 BTUs. Okay. So 1 cubic foot of LP is 25,000 BTUs. Now, LP is a little different because we don't buy LP by the cubic foot. We generally buy it by the gallon. Okay. So one cubic foot of LP is 25,000 BTUs. So if I have a 100,000 BTU furnace, okay, how many times does 2,500 go into to 100,000? 40. So I need 40 cubic feet of propane an hour. So 40 times 25 cubic foot of air equals 1,000 cubic feet of combustion air. All right. Plus 50% more for dilution air. So half of 1,000 is 500. So I need 1,500 cubic foot of combustion air for this furnace. All right. So total combustion air again, I need 1,500 cubic feet. So 100,000 BTU furnace divided by 2,500 BTUs per cubic foot equals 40 cubic feet. 40 cubic feet times 25 cubic feet of air per foot is 1,000 cubic foot of air. 1,000 times 50 for dilution air is another 500. So 1,000 plus 500, I need a total 1,500 cubic feet of combustion air for this furnace. Do I have it? All right. So again, just to visualize it, so LP is a little different than natural gas. Now, 1 cubic foot is 2.5 times as much BTUs, but it also requires 2.5 times as much air. All right, so if those, again, picture those blocks as being 12 by 12 by 12. All right, that's a lot of air. Okay, so in a small enclosed space like we looked at in the previous slide, that little 10 by 8 room, 10 by 10 room, we'll need to bring air in from either an adjacent space. So I might have air vents to the basement, providing the basement's large enough, or outdoor air could be brought in. All right, so we're going to bring air in from outside. Okay, so it could be, you know, X amount of air outside, and you'll get into homes that you'll see this. There's an air vent coming down next to the furnace. We're bringing air in both the floor and up at the ceiling. Okay, and there's a requirement for how much that's going to be. So in a large room like an open basement, combustion air may be taken from the basement. In smaller rooms, we might need to add. Now, all this combustion air is coming from someplace. So it's going to come in around cracks. It's going to come in through window leaks. It's going to come in through doors. Modern furnaces now, we bring combustion air in specifically for the furnace to eliminate this problem. But a lot of this equipment's still there. Water heaters, a dryer, a gas dryer requires combustion air as well. So the calculation can be the same. We still have to make up. So now we got the furnace plus the water heater plus the dryer in the same room. So we need to calculate the combustion air for all of them because they all need it. Okay, so again, on the modern high efficiency furnaces, we're bringing the air in specifically for combustion. So we will, you know, talk about that here in a minute. So combustion analysis, this is another thing that's come a long way. This thing over my head is this is a combustion analysis kit. Nowadays, we can test the combustion. We can see how the furnace is running. What is our efficiency rating? You know, what is our excess oxygen amount? Do we have CO? What's our CO level? Mostly we're going to have a little CO, but it shouldn't be much, and it's going to be measurable. So combustion analysis is going to tell us, is our fuel pressure too low? Are we venting properly? Are my heat exchangers cracked? Okay, we haven't even gotten to heat exchangers yet. We're going to talk about a cracked heat exchanger because generally a heat exchanger is going to pull air in. So we can screw up the whole combustion with cracking a heat exchanger. Blocked or obstructed flue. What if my chimney's not venting properly? What if I don't have enough combustion air in that little space? We're going to mess up our combustion. So low or no makeup air for combustion. We'll also be able to see that from this little test. So we're not going to get too in depth in this, but I just want to show you what it is. So we're going to take our little device. We're going to measure our flue gas. We're going to measure temperature, and we're going to actually take a sample of our gas. So if I look over there, you can see fuel, natural gas, O2, 5.4%. O2, that's water. Then we get into CO2, 8.8%. Okay, we're good with that. Carbon dioxide, 12 parts per million. That's coming out of the vent. All right, so on a good running furnace, that's a decent number. Obviously, the lower the number that is, the better. Flue gas, that's Celsius, 55 degrees. Inlet, 17 degrees. But let's go down to efficiency. It says that furnace is running at 99% efficiency. Wow. So for that cubic foot of natural gas that we paid for, I'm getting 99% of that heat in the house. Okay. So all the things that this combustion analysis tells us. Now from, you know, again, it's just all the stuff we just looked at. Gas pressure, gas volume, combustion air, dilution air. Do we have enough? Do we have the proper mixture for proper combustion? All right. And this is how we check it. We used to have a pretty involved way of testing this with the old draft gauges and smoke spot on the oil burners. I mean, that was all great stuff. But nowadays we have CO detectors or CO analyzers like this one. So we can actually measure our combustion and it'll actually print us a report. Okay, so if we're not getting the right numbers, each manufacturer has a CO level they'll allow, and if it's too high, then we have to address it. Now you guys are experts at it, right? What do I know? I know I need the right amount of gas. I need the right amount of air. If I have the two, this comes out like that. If that is off, I have a problem. Too much air, not enough gas, or too much gas. Right? So the balance of that is wrong. It's pretty much that simple. Okay, so CO, if I look at this little chart, remember we had that CO detector I showed you earlier, and you can see right there, 50 parts per million. For healthy adults, you have to decide whether you're healthy or not. We're allowed to be in a room in that environment for 8-hour period working, and it's not going to be harmful. Now look at 200 parts per million. Now think about that, a million, 200 millionths, 200 parts a million. Slight headache, fatigue, dizziness, nausea after 2 to 3 hours. Right? After 200 parts per million. 400 parts per million, frontal headache with 1 to 2 hours, life-threatening after 3 hours. Okay, 800 parts per million, dizziness, nausea, convulsion, after 45 minutes, death within 2 to 3 hours. Okay, so again, we don't want to be afraid of this. Education is everything. We need to understand this. Okay, we can prevent this. This is simple to prevent. All right, that perfect combustion we talked about, we need to understand that. We need to address that. We take care of this. All right, it's pretty much that simple. Do I have enough combustion air? Do I have the right amount of fuel mixture? Perfect. Are we venting properly? All right, so British thermal unit. We always hear, you've heard me say this several times today, BTU. Now, it can also mean, here's a really bad joke if anybody said in my class before, BTU could also stand for beer that's undrinkable, which we all have a different opinion of that, but if it comes from Milwaukee or St. Louis, it's my book, it's BTU, but whole different story. Anyways, BTU, British thermal unit. All right, what does that mean? Now, this is a term we throw around wildly in our industry, right? We talk about air conditioners, 24,000 BTUs. We talk about a furnace, 100,000 BTUs. The amount of heat required to raise the temperature of 1 pound of water, 1 degree. Huh? If I have a pound of water and it's 70 degrees, it takes 1 BTU to raise it from 70 to 71. Okay, 1 BTU. So let's take a deeper look at that, because everything we do is based off of this. All right, so a gallon of water weighs 8.36 pounds. All right, so that's 8.5 pounds of water. We're talking about 1 pound of water. So how much is a pound of water? So if I look at this, I have 1 pound of water, which is this bottle of water. We've got it weighed out, and you look at a little scale, it's about 1 pound. So it's about it's about 1/8 of a gallon. And that bottle of water is 75 degrees. I need to add 1 BTU to take it from 75 degrees to 76 degrees. 1 BTU. So that 100,000 BTU furnace is 100,000 of those in an hour. Okay, so let's take it a little further. There's my teapot sitting on my stove. It's actually not my teapot, it's not my stove. I do have a teapot and I do have a stove, but that's not mine. All right. It takes the same 1 pound of water at 76 degrees. I place it on a burner. I raise it from 76 degrees to 200 degrees. So I'm making coffee, not a tea drinker. How many BTUs did I have to add? That's pretty simple. I'm going to take the 200. I'm going to subtract the 76 from where I started. And I have 124 BTUs I just added to that water. It's that simple. Okay, that's what a BTU is. Everything is based off of that. So now when you look at a burner, and like I got a burner on my stove, my high output burner is 30,000 BTUs. That's a lot. I can raise the heat of a lot of water, a lot of degrees, right? Okay, so kitchen match. Think of the little wooden kitchen matches, not the little paper ones, but the wooden kitchen match, like the old Ohio blue tips that used to light on everything. That is roughly 1 BTU. Okay. Now, I was talking to somebody recently about how I'm a geek. We were both talking about, we're both geeks. Well, I found this picture and this doesn't scream geek, nothing does. All right. Online, I found this picture. This is 90,000 matches. All right. So that is 90,000 BTUs. Now, I got a little overexcited when I saw this picture, knowing there's somebody else out in the world who would actually think of doing this just to see it. Okay, but that is 90,000 of those. So that is 90,000 BTU furnace in an hour. That's the amount of heat it gives off. Okay, I'm sorry, it just was pretty exciting when I found this. So, but anyways, the heat of one kitchen match or the amount of heat required to raise the temperature, 1 pound of water, 1 BTU, or some nut who puts 90,000 matches together. I didn't do it. That's just because I never thought of it. So anyways, that is what 90,000 BTUs looks like. So that furnace we looked at, the first one, the natural gas furnace, that's how much heat it produces in an hour if it ran for a straight hour. Okay. So how many BTUs would it take to raise the temperature of 1 pound of water, 1 pound, I got to fix that, 1 pound of water from 100 degrees to 200 degrees. All right, so I got 100 degree water. I need to raise it to 200 degrees. So I need to add 100 BTUs. Okay. If that is, from there, I can determine if it's a bigger amount of water, but it's that simple. So hopefully that makes sense. So it'll take 100 BTUs to raise the temperature of 1 pound of water from 100 to 200, 1 BTU per pound. And again, we can build off of this. When we get into boilers, we can determine pump size and everything else. It's all based off of this. Okay. So how many BTUs? So it would take, let's see. So how many BTUs would it take to raise the temperature of 5 pounds of water, 100 degrees? So if I got 100 degree water and I have 5 pounds of water, which is about 3/4 of a gallon, how many BTUs would it take to take it from 100 to 200? So 500 BTUs to raise that temperature. All right. Obviously, when we're heating water on a stove, it's not all going into the water, but you get the gist of it. So that is what a BTU is. See, now if you didn't learn anything else today, it's that. Now it's everything. It's what we do. We add and remove BTUs. If I had to sum up what we do in heating and cooling, we add and remove BTUs. That's heating and air conditioning summed up right there. Okay. So we talked about gas, we talked about combustion. Now we're going to get into fire. So we're going to start talking about venting. Now, could you put this fire inside your house? Yeah, but your house isn't going to last very long. Unless you live in one of them, like the Native Americans did. They built the great big council chambers, and they had an opening in the middle for the smoke to go out through the roof. Okay, but if you built this in the living room, you're going to burn your house down. Because we have to have somewhere for that smoke to go. Now, this is nowhere near complete combustion. We've got a lot of yellow coming off there. We have a lot of smoke. If you ever stood around a campfire, you know the smoke that's coming off of there. So we got to get rid of that. Secondly, this is in one room. How do I distribute the heat around the house? Okay. How do I control it? You're cold, stoke up the fire, throw another log on there. All right. So then we come up with the fireplace. Now, fireplace is actually a pretty cool feat of engineering once you understand the whole thing. So we make the stone fireplace, which is fireproof. We build a fire in it. We have a chimney to take the vent gases out, the flue gases, smoke. But it's heating. But it's only heating out in front of it. So if I'm sitting in that couch right there, I feel the heat. In the immediate vicinity, I feel the heat. If I walk in the next room, it's cold. Because we learned a word today, combustion air. Guess what? That fireplace uses combustion air. And where's it coming from? It's coming from this house. So we're actually taking air out of the house, and we're heating up that chimney to feed that fire. All right, no control. We're only heating the space we're in. Then, pretty famous American came up with the idea of a potbelly stove. I'm not going to tell you it is. There'll be a quiz at the end. Okay. And if you look at that stove, now what did that accomplish? Well, now I can move the fire into the middle of the room. And if I heat that stove, it can give the heat off in all 4 directions. Yet the fire's contained inside, and then there's a flue pipe that takes the gases outside. That is the first heat exchanger. All right. What is it? What am I talking about? Well, I've got fire contained in the inside. All the smoke's contained. It goes up the vent pipe. We're transferring the heat through the steel to the surrounding space. So now I can put it in the middle of the room like that gentleman over there sitting in front of it, and we're heating the whole room. I can put multiple stoves in different rooms. And now I have a little bit better space control, but I still need a stove in multiple rooms. Control, well, we talked earlier about combustion, right? If I reduce air, I reduce combustion. So I can cut down the air, primary air. I can cut down the flue vent speed. I can slow down the combustion. All right, it's all contained inside. You can see it's yellow flame, so there's all kind of nasty flue gases coming off that, but we're putting out that. So let's talk about chimney for a minute. This was actually a fairly ingenious invention, and it's not just a pipe sticking up through the roof for flue gases to go through. There's actually quite a bit of science involved around the chimney. Now, first of all, the chimney is the tallest thing around for a reason. Okay, that's to ensure we have a draft. Now, if I look at that picture over there, you can see the cold air coming down, right? Because cold air sinks. Hot air rises. All right, that's physics. So the cold air falls, hot air rises. So if I make this big, tall chimney and the hot air is going to rise up through that chimney, what happens as the air rises, the cold air is going to fall to replace it. So I start to create a draft. All right. There's actually a suction on that chimney if the chimney is built correctly. If the chimney is tall enough, there's no obstructions around it, because as the warmer rises up that chimney shaft, the cold air comes back down to replace it, and we create a draft. We start a flow. All right. If you look at this one here over my shoulder, you can see this is a Class A chimney. This would be a wood stove, but you see it's extending beyond the peak of the house. All right, that's the key. It's got to be higher than anything else around it for this to all to work. All right, but it is a pretty ingenious device. All right, so we look at all these different chimneys. They're doing the exact same thing. They're the highest thing around. They create this draft, okay, because as the heat's rising up the chimney, the warm air is rising, the cold air is replacing it, and we create this draft. All right. The example I had earlier, there was a guy holding a match in front of a draft diverter on a gravity vent water heater, and it was drawing the smoke up. These will draw the smoke up, all right? Because if they're designed properly, now if that chimney's too short or there's something tall around it, it might stop it. Okay. So these are masonry chimneys. Nowadays, incredibly expensive to build. Plus, they're not tremendously effective because we don't really use them that much anymore. So what we ended up doing, and we're going to make it cheaper, right? So we went to B-vent chimneys because they're a whole lot less expensive to put in. Most modern houses use B-vent chimneys as opposed to masonry chimneys. And what it is if you look at that little diagram there, it's a double wall pipe. So you have aluminum inner wall, galvanized metal outer wall. There's about 1 inch of space between them. Okay. And that is a B-vent chimney. So the outer wall doesn't get as hot as the inner wall. All right, so we don't start fires. So if you look at this picture over my head, you can see how that's passing through the house. It's a double wall chimney. It's called B-vent. All right, so that allows us an inexpensive way to put a chimney in. Now, gas-fired appliance is going to run maybe 500 degrees hottest flue gas. Modern ones are going to be much lower than that. So this can handle it. You couldn't put a wood stove on one of these. A wood stove would require a Class A chimney because it's much hotter. So these are tested to around 500 degrees. All right. So they come in predetermined lengths. We don't cut them. They lock together. This is basically the layout. So you got special elbows that are double walled. You have special pipe. You have special fittings to pass through the wall. You have fire blocks, flashings. Okay, so natural draft, we kind of talked about this a little bit earlier. And if you look at that on the left there, again, they got gentlemen holding the match to the draft diverter. Okay, and if the chimney is correct, it will actually pull the smoke straight up. You can feel the draft. That's one of the tests we used to do. Back then, actually, we'd use a cigarette because we could smoke and, everybody did. But you have a draft. Okay, so over my head here is, again, the natural draft furnace with the draft diverter. That's where your dilution air comes from. And then if I look right here, you can see fresh air. All right, they got a flue pipe coming from outside. The cold air can come in. They put this little elbow here because cold air sinks or doesn't rise, right? So that's supposed to help keep from creating a cold air draft. but that's a way of bringing fresh air into the room to feed that furnace. Okay. So again, I'll look at matches around a draft diverter on a water heater, and you can see the smoke being drawn up there. That's a properly functioning chimney. Okay, somebody did their work right. All right, so we created this wood stove. Problem with the wood stove is it sat in the middle of the room. We had to have multiples. So my grandmother had one of these in the house she lived in. This is a gravity furnace. This was really early central heating. And there's a sheet metal jacket basically around what's no more than a metal wood stove. Okay, so if I look over there, you're gonna see I got a fire door. That's where I stoked my coal. And then over here, you can see the sheet metal jacket with this huge ductwork coming off of it. And right here, this big pipe is the cold air return. Cold air naturally falls. And all the pipes are on a diagonal heat rises. So the heat just naturally rose to heat the space. The cold air would fall back in this return. This little guy here, that's a humidifier. It's just a little spot to put water. This is the flue pipe right here. And you can see the little draft diverter opened to the basement. Because we dilution air, remember? Now you're an expert on dilution air and makeup air. And then you can see there's some dampers on those ducts. That's how we controlled room temperature. We can damper them down. So there's a little bit better picture of it over there. And you can see the yellow pipes. You can see the yellow, that's the space between the jacket and the metal, basically wood stove inside it. It was usually cast iron. So you'd heat up that metal inside. The air would pass around the outside, pick the heat up. By gravity, it would pass into the rooms. So you can see the ductwork's always going on a diagonal upward. And then the cold air would, by gravity, come back down that return, back into the furnace. Okay, this was a gravity furnace. There's still a handful of them out there. There was no blower, not tremendously efficient. Most of them were coal converted. Again, there's still a lot of them out there. But this is the next phase of furnace development. But again, that inner portion is still a heat exchanger, just like it was on the wood stove. All right, so here's just another look at it. There you can see it kind of being taken apart up there, where you got the inner basically metal wood heat exchanger where the fire was built, and then you got a sheet metal jacket around it, air passed around them. Okay, that picture over there on the far on my left, you'll see is just another gravity furnace, and it's hard to see it, but there's actually a conversion burner on it where they converted it to natural gas. If you ever see the movie Christmas Story, one of my favorites, and there's a part where the father's messing with the dampers on the wall and he starts yelling about the clinkers. Clinkers were left from burning coal in that gravity furnace. So that's what he was doing. He was adjusting the draft on that gravity furnace. All right, then we went to forced air. That was gravity. Now we're into forced air. This is currently where we're at. So forced air actually uses a blower, which this is an upflow, would be in the basement. So most of what we do is like this. You see the blower in the bottom. Heat exchanger is above the blower. So now the blower comes on and it forces air through the heat exchanger. We heat it, we distribute it to the house, and it comes down the return back to the furnace, but it's all done by fan power now. Okay, so we still have a heat exchanger. We've changed them up a little bit, but they're still doing the same thing. The combustion is inside the heat exchanger. We're exchanging the heat to the outside of the heat exchanger to separate the smoke or the exhaust or products of combustion from the air we're heating. All right, so the one in the center, it's a big old tank heat exchanger. This would have been an older style furnace, old low boys, we used to call them. The one on the left and the one right over my head, this is a modern clamshell heat exchanger, but it's the same concept. If you look over there, you can see the burners in the bottom. The flue gases go up through it, and then they come out the top to the gravity chimney. So the flames are inside that metal heat exchanger. The air is passing on the outside. So we're exchanging the heat from the flue gases to the air. Obviously, if these get a crack in them, we have an issue because then we can start to leak. All right. So one of the next changes, because we talked about gravity, right? Gravity burners, and remember the gravity burners, like here, if you look at that furnace over there, the burners are in the bottom of the furnace. All right, and the burners stick into the heat exchanger, and the flue gases, heat rises naturally through the heat exchanger, and then we have the draft with the open chimney on the top. Now, next thing we got into is modern 80% furnaces. We no longer are, we want to control a little bit more of that combustion, right? Because before, remember, the chimney drew air through there, and we had a lot more just left to chance. So now we're going to use a draft assist, or draft inducer is not really, this is more of a draft assist. Okay, we're still using a gravity chimney. So, remember the chimney or the B-vent chimney with it? We're still using a chimney. So this is assisting the draft. Okay, because we've lost, this took the place of the draft work. But what this did was control the rate at which the flue gases are passing through that furnace. Okay. So we were able to get more efficiency, right? Because we needed to squeeze more heat out. Because this old furnace over here on the right, or that one in the center, those might have been 60% efficient or less. Now we're getting in the 80s with this fella. Okay. And if I look on that furnace over there, you can see it's at the top. The burners are still in the bottom. So it's drawing the flue gases from the top of the heat exchanger. The burners are still sitting in the bottom. And then from there, it goes into a chimney. Okay, so this is a draft assisted. Okay, we still are using the chimney. Okay, so if I look here, this one right in front of me, you can see standard masonry chimney. You can see the 80% furnace and a standard water heater with the draft diverter, the dilution air. One in the middle, same thing. I got 80% furnace, but the water heater is a draft diverter and it's going into a B-vent chimney. So I still need a chimney. So we still got to worry about dilution air. We still got to worry about combustion air. We still got to worry about the draft on the chimney. Okay, we're still sucking air out of the house that we're heating to go up these chimneys. Okay, so draft assist, 80%ers, still uses a chimney, but no draft diverter. So all that dilution air we used to pump in through the draft diverter is now happening from that little fan. We can't go out a sidewall. We have to go into a chimney still. B-vent, all the way, some cases is required. Flue gas temperature is much lower. Well, how did we get from 60% efficient to 80% efficient? Well, because I can control the rate at which my flue gases pass through that furnace, I can squeeze more heat out, right? So now instead of 60%, I'm getting 80% of the heat. So they're more efficient, so the flue gases are much lower. Okay, now remember we talked about flue gases. One of the byproducts of every flue gas we talked about was H2O, water. And that one, and we had like 200 cubic inches of water coming out of 100,000 BTU. That's a lot of water. Well, do you see water dripping out of your chimney? No, because it's water vapor, right? It's in a vapor form. But if we cool that gas too much, that water can start condensing. Okay, so in an 80%er, we're cooling that flue gas, but the water is still vapor. Okay, so we're still using building air for combustion. So heated air is coming out of the building. Can no longer use a standing pilot. We don't have a chimney or a draft. Efficiency is up to 80%. Still using single stage or primary heat exchanger. So a single heat exchanger still. And we'll talk as we go on here. All right, then the next change was we went to a 90% furnace. All right, so what that's telling us is at least 90% of the heat we're paying for is going in the house. We're not wasting 40% anymore. We're only wasting 10% or less. We no longer need a chimney because we have a draft inducer. All right, we don't have a draft assist anymore. We have a draft inducer. We're inducing a draft. We're actually forcing the flue gases through that heat exchanger, and we're forcing them outside. So we can sidewall vent. So if you look at that picture over there on the top, we're using sidewall vent. But now we're going to squeeze that so much heat out of that. Remember all that water vapor that's in there? We're going to get flue gases down to 100 degrees. That water vapor is going to start to condense. So we're actually going to get liquid water coming out of this furnace. Because remember, H2O is a byproduct of combustion. When the combustion gas was 500 degrees, it stayed vapor. When the combustion gas was 300 degrees, it stayed vapor. Now the combustion gas is 100 degrees or less. It's condensing back into water. All right. So one of the things you'll notice on this furnace is they're using plastic venting material because there's water going to run through it. All right. And it can't be metal. It'll rust, obviously. It'll leak. It has to be watertight. It has to be waterproof. Second thing, I see two pipes. And on the outside there, I see two pipes because all that combustion air, remember that 1,500 cubic feet of combustion air I needed that I would have used to draw to this basement? It's coming from outside now. So now I'm not going to take all this heated building air and throw it in my chimney. I want to bring the air in from outside. So all the combustion air, any dilution air, which I really don't need anymore, is all coming from outside. Okay. So the in-shot burners. So the in-shot burners came along when we added the draft assist and the draft induced. Okay, because now I'm actually pulling the flue gases through this heat exchanger. So I don't have, are gone are the burners that stuck inside the heat exchanger, the old ribbons. We've gone to in-shots like this. Okay, so now if I look at this heat exchanger over my head, you can see the top. I still have the serpentine clamshell, which is like I've had on many furnaces. But now underneath it, I have a second heat exchanger or a secondary heat exchanger. So, because back in the first 80% furnace, with this, I'd go through my primary heat exchanger over there. 300-degree flue gas would go through this vent motor up the chimney. So now what I did is we're going to invert our setup here. And the burners are going to go at the top because we're doing draft induced. Now we're forcing the flue gases, so we don't have to worry about gravity anymore. We're forcing the flue gases through there. So they're going to go down through that heat exchanger. And instead of going outside, they're going to go through this secondary heat exchanger. So now we might have 250-degree gas going into this bottom heat exchanger or secondary. You look at the one over there, it's actually like a coil. And here it's really narrow little fins. And the blower is right underneath that. So the cool house air coming from the blower is going to hit the secondary heat exchanger first, which is about 250 degrees. All right. Going to cool that, and then it's going to go across the hotter part of the heat exchanger. All right. So if I look, here's a 90% heat exchanger. In the picture over to the left there, you can see where the burners were at the top. You can see the discolored spot in the heat exchanger. That's where that in-shot burner flame was hitting. Or wasn't hitting the metal, but just where the most concentrated heat was. And then the fan is forcing all that flue gas through that primary heat exchanger, exchanges heat to the air. Then we're going to come out the back over my head here. This is a collector box. The gas is going to come out of the primary heat exchanger. It's going to go down to the secondary heat exchanger. The draft inducer is on the front, which is going to pull it out. So if I look in the center picture, that little triangle shape, that's where the fan would be. So it's going to be pulling the gases through. So it'll pull them through the secondary, out the vent. So that secondary heat exchanger, the lower one, the flue gas is only going to be about 200, 250 degrees. And then that house air is going to blow across that first. We're going to squeeze almost all the heat out of there. So the gas coming out of this is about 100 degrees, gas and water. So again, the burner's at the top, goes through the primary, through this collector box above my head, into the secondary, out to the draft inducer and to the vent. All right. And we're squeezing almost all the heat out. Now, 90% or plus, we got a 97, 98% furnace now to where 98% of the heat is coming into the house. Okay. Now you can see that heat exchanger over there on the far left has actually got a crack in it at the top there. Okay. Now, crack, obviously we can leak flue gases into the house. More likely we're going to suck house air into the heat exchanger because the heat exchangers are generally under negative pressure. So again, that center is where my draft inducer is on a 90%er. So in draft induced, 90%er, plastic pipe. No longer requires a chimney. 80% still does. Creates positive pressure in the vent system. So the furnace is in a negative pressure, but the vent pipe is a positive. Can be sidewall vented with PVC or other products also available. Now, you want to be careful with that one because certain things can't be used with PVC. We've had to go to specific plastic for certain boilers require a specific plastic venting. The PVC may go away because I know there's some talks about that, but currently 90% furnaces, we still use PVC pipe. Why? Because the flue gases are so cold that we're condensing and they're waterproof. Utilizes primary and secondary heat exchanger. Squeezes almost all the flue gas, up to 98% of the heat is getting squeezed out. Flue gas temperatures down to 100 degrees over starting at 500 early on. Water vapor and flue gas is condensed. That's also why they're called condensing furnaces. The furnace requires a drain. Can supply its own combustion air from outside. So we have a 1 pipe or 2 pipe system. So the 2 pipe would have 2 PVC pipes, 1 vent, 1 intake. So we can bring all that air from outside. No longer uses heated air from the building for combustion. Okay. So here's a better look at it. You can see up front there's my draft inducer. All right, there's my PVC pipe. You can see the burners up at the top. Here's a little animated look at it here so you can get a better look. So the burners are at the very top, the in-shot burners. Flue gases go through the primary, through the collector box to the secondary, out the vent fan here, the draft inducer, and out of the house. And there's a little pressure switch you can see there in front of the fan. That proves that that fan's running before we fire it. Okay, so a modern 90% furnace. Venting is very specific. So whatever brand furnace you're dealing with, you got to get the chart they're going to provide is going to tell you what size pipe, depending on how long it is and what size the furnace is. Okay. We can do 2 pipe. So if I look at that picture over there, I have 2 pipes. I have my intake and my exhaust. What I have over there is a concentric, which the intake is on the outside, the exhaust is on the inside. Or over my shoulder here, you see a furnace, which the center pipe, or the pipe to the left, is drawing air from the basement. Okay, so we can still do that, but it's wasteful. We're using heated basement air for combustion. All right, so there's the heat exchanger, the advancement of the furnaces. Okay, so now let's take a look at how we make all this work. So above me again is the in-shot burners. That's modern draft induced furnaces. Above that is the old ribbon style burner that went into the heat exchanger for the old gravity vent. The first thing I had to do is light this thing. So we're gonna look at some basic controls. There's my gas meter over there, right? I got to regulate it. I got to send it to this burner. Again, this would be an old conversion burner that might be in that gravity furnace over there. It was Columbia made them, Barber made them. I'm way too old even knowing that I worked on them, but I did. Anyways, so if I just had a gas valve and a pilot, right? We got a pilot light sitting there. We light the pilot and a gas, and I open the gas valve and the furnace comes on. Great. What happens if that pilot goes out and a gas valve opens? I'm going to build up gas, get above its explosive limit, and boom. All right, so I have in this scenario, I have no safety at all. Okay. And it's a manual shutoff. I'd have to manually open and close this. So how do I do this automatically? I also have to regulate it. Remember the gas pressure regulator? So the one on the meter will drop it down to about 7 inches. And then the one at the appliance will take it down about 3.5 inches. So we had what was called a gas control. So we had a regulator and we had a gas valve. The electric gas valve, open and closed. Now, how's that valve work? All right. This is the simplest way to think of it. You probably did an experiment like this in grade school, right? You took a nail, wrapped the wire around it, grade school, Cub Scouts, whichever. Wrapped the wire around it, attached it to a battery, and you turned that nail into electric magnet. Okay, that's exactly how our gas valves work. Solenoid, that's the fancy term for electric magnet. So we have an iron core, we wrap a wire around it, we put voltage to it, it creates magnetism, which pulls a valve open. All right, so this picture here is a simple look at a basic furnace control system. I have a thermostat at the top. Thermostat is a switch, right? Makes electrical contact. So thermostat closes, we need heat. It sends voltage to that little electric magnet there. It pulls the valve open. Okay, now we have 110 volts coming into the wall outlet, like over there. And if you to stick a screwdriver in that, you're gonna do just like this guy's doing. So I'm not telling you to do that. Don't do that. But remember in our example, we were using a battery and I could touch the battery, right? I can physically touch that battery. It's not gonna, because it's only 1.5 volts there. So we're gonna drop the voltage down to 24 volts. And there's a number of reasons. I don't need electrical permit to mess with 24 volts. It's much safer. Unless I touch my tongue to this transformer, I'm not going to get a shock from it. If you put your tongue across those two terminals, even and wet your fingers, you'll get a little tingle. But so 24 volts is much safer. The wiring is much smaller. I don't need to use real heavy gauge wire. I don't need conduit. It's cheaper to run. I need to have a permit. Doesn't require conduit, doesn't require greenfield. All the components are small. Okay, if my little electric magnet here was going to be 110 volt, like you have coming out of the wall, it'd have to be much heavier, much more expensive. But because I'm going 24 volts, everything is smaller, everything's less expensive, everything's safer. So up at the top there, you see my transformer. All it's doing is taking 110 volts, I'm dropping it to 24. We call it control voltage. And again, it has to do with safety. It's just more effective to use. Everything is smaller. So I step down from line voltage to 24 volts. Then I go to my thermostat. Now, what's a thermostat? It's a switch. All the switch is a contact, right? So I take my 24 volts, the switch closes. Now my power can go to my electric magnet. In your picture there, the guy's holding the magnet on the battery. So it's like take one end away and touch it again. That's what the switch does. So the thermostat closes. We send 24 volts to the magnet. It pulls the valve open. Burner comes on and it lights. Hopefully, providing that the pilot's lit. Okay. Well, what happens if the pilot's not lit and that burner, that valve opens? Okay, we're gonna have an explosion, right? Because we can fill the house with gas. So now we need to prove the pilot's on. All right. So what happens if the pilot goes out? The main burner will come on with nothing to light it, and we can get boom. So we needed some type of pilot safety. So the next thing we come up with is a thermocouple. Now that's the thing in front of you. We still use them on water heaters. You'll still see them out there in all unit heaters. But a thermocouple, if you look at the picture over my head, at the top, it's a safety shutoff circuit thermocouple. Thermocouple is a coupling of two different metals that when heated generate a very low voltage. So remember that electric magnet we made with the nail? Well, I'm going to do the same thing, but I'm going to use voltage that's being generated from that thermocouple. So you heat it, it creates a very low millivolt. I feed that to the pilot safety, which one of the two up there. So if the pilot goes out, the safety opens and it doesn't allow the main valve to come in. All right, so it's pretty simple. It's really pretty ingenious. You think about this stuff was created 100 years ago. So in this case here, my 24 volts comes down, my thermostat closes, it goes to my pilot safety. My thermocouple's lit, so I have voltage holding that magnet in, and a little switch is closed. So power comes to my valve opens, gas comes out, I light the main burner. If the pilot goes out, I can't get power to the main valve. All right, so a thermocouple is about 30 millivolts. Okay, so again, it's just two different types of metals. There's a cold joint between them, and when you heat them up, they generate a DC voltage. So when you light your water heater here, and you got to put it to pilot and hold that little red button, you're waiting for that little thermocouple to heat up, create its 30 volts, millivolts, which now hold this valve open. All right, so that's what you're waiting for. So 1 millivolt is or 1 volt is 1,000 millivolts. So I got 110 volts in the wall socket. So that's 110 times 1,000. All right, so 1 millivolt is very, very, very minute. It's a very small amount. So again, a good thermocouple is going to put out about 30 millivolts. Okay. So standing pilots were simple. We had some type of pilot safety. There's various different types. The thermocouple is probably the most widely used. We just talked about. Up above there, that's a mercury in there. Obviously, we can't use mercury anymore. And there's a switch there. So you heated that up, the mercury expanded, it flipped the little switch. All right, down here is the one a little closer to Bryant's heart. We still have the old 3-wire pilot. It's a bimetal. Okay, what's a bimetal? 2 dissimilar metals that expand and contract differently. So in the picture there, as it heats up, it makes or breaks a contact. So the bimetal pilot had a bimetal, and when the pilot was hitting it, it would trip a little switch. So we knew we had the pilot. Okay, so we have our gas shutoff valve, right? We have our regulator to drop the pressure. We have our gas valve. We have our pilot safety. Okay, that was called the gas train. Now you're going to hear the term combination gas valve. That's this guy. What that did is combined all that stuff together. So we got a pilot safety built in, we got a regulator built in, we got a shutoff valve built in, we have a main gas valve all built in. So now the thermocouple goes to it, the pilot goes to it. So there we go. This is an old style furnace. You can see the old burners with the air shutters for adjustment. The burners go into the heat exchanger. You see down at the bottom, the standing pilot. You see the thermocouple going back to the main valve. You see the transformer off to the left there. There's the valve, there's the fan limit control, there's a transformer. All right, limit control, well, because if the furnace, now we have a pilot safety, we need to shut the furnace off if it gets too hot. Okay, so the limit is, we already talked about what a bimetal is. It's set at a certain temperature. If the furnace gets beyond that temperature, that little metal warps the 2 different metals and it opens the switch. Okay, so it protects the furnace from overheating, shuts the main burners off immediately, protects the low for low airflow, high gas pressure. So we're using a bimetal limit control. So if we look here now, transformer limit, high temperature limit, thermostat, our combination gas valve, and look at, there's our cap tube, there's our combination gas valve. And so on a call, providing the limit is not hot, we're going to get 24 volts to the valve. As long as the pilot's lit, we're going to light the valve. Okay. Now, one thing we're missing here is we don't have a means to turn the blower on. So early on, we used a temperature limits or a temperature blower switch. So just like the limit, if it got too hot, it opened the switch. Well, as the furnace heats up, a bimetal closes the switch to turn the blower on. So many cases, we combine the limit and the fan control together. So at a certain temperature, it starts the blower after the furnace warms up, so we don't blow cold air around. After the burner shuts off, the furnace cools off. It shuts the blower back off again. So now we're getting a little bit more involved here. So if we look here, so now I have my 24 volts. I have my combination fan limit control. So my 24 volts goes through the limit to my thermostat. And then I also have my power going to my transformer coming from my limit. So if the limit opens, it kills everything. So thermostat sends 24 volts to the valve. The thermocouple's lit, the valve opens, the burner lights. As the furnace light heats up, you can see now I have power going to my fan and my blower comes on. If my limit were to open, it would kill 24 volts to everything. All right. Now, again, as we progressed into more efficiency, pilots were expensive, right? Because you had to keep them running. You know, one pilot at, 100 BTUs isn't much, but how many millions of pilots were going around the country? So the next thing we wanted to do is get into intermittent ignition. We didn't want a pilot anymore. That's not one that was lit all the time. So we wanted intermittent ignition. So it lights the pilot only when we need to light the furnace and then shuts it off again. saves fuel because we only light the pilot when we need it. When we got rid of the draft, remember the big chimneys? We had a draft. When we got rid of those, we can't have a pilot anymore because there's no vent anymore, right? There's no draft. So we had to come up with new pilot safety components. We had to come up with a way to light the pilot. We had to come up with a new style gas valve. Thankfully, electronics came along. So that helped. So now we have what's called the redundant gas valve. So it's kind of similar to the combination, but remember that we don't have a pilot safety in it anymore. So we have a shutoff. We have a, we have a shutoff. We have a pressure regulator. We have a main valve. We have a pilot valve. Okay, they're both electric. So now we've come up with an ignition control module. All right, because again, this was early on. So we still have a fan limit. So as long as the limit's closed, it sends power to the transformer. Transformer is powering, sending power to the ignition and then the thermostat. And so when the thermostat calls, it sends power to the ignition module, say, hey, I need fire. 24 volts goes to the pilot valve. The pilot valve opens, sends gas to the pilot. The igniter starts. We have a spark plug over my head, just kind of like in your car. It makes a spark, it lights the pilot. A flame passes through the pilot, or a current passes through the flame to ground, and it tells that controller over there, I got a pilot, open a valve. So it says, I got a pilot. It now, the control sees that we have a pilot, we open the main valve. The burner comes on, we heat up the furnace, the fan limit control comes on, and the blower starts. If the pilot goes out, if the pilot doesn't light, then it shuts everything down. Okay, so it'll just try that, if the pilot doesn't light, if the flame goes out, if the limit trips, it just drops everything out. Okay. So again, if the thermostat calls, we power it up, we send a spark, the pilot doesn't light, it drops out. It doesn't go any further. Okay. Then we started with direct ignition. So now the pilot was still a problem. So now we're going to get rid of the pilot. We go to most everything now uses direct ignition, hot surface igniters or spark igniters, which is what you're going to see mostly nowadays. So we don't need a pilot. We're going to light the main burners directly. So most modern furnaces use them. We've eliminated the pilot. We've eliminated a step. So we have two main types of direct ignition. Hot surface uses a hot surface igniter that glows, or we use a spark, like a spark plug, but both directly light the burner. So this is hot surface. So these are different. They're fairly fragile, so you want to be careful handling them. Most of them are 110 volts. Some of them are 24. There was the oddity over here, which was the Honeywell smart valve, which was a 24 volt. We're not going to get into that too much. They all pretty much work the same. So light the main. So what happens is they light the main flame, the main burner directly. There's no pilot. So the igniter will come on first. The valve will open. We'll light. If we prove, then we continue through a flame rod. We tell that the flame is lit, and then we move on. So if I look here above my head, you'll see hot surface ignition. That's the igniter. Over there, you'll see the flame sensor. Now, if you look in that picture there, you can see the flame sensor sticking down into the flame. Now, a lot of guys really misunderstand the sensor. Again, I know we're still just kind of getting your feet wet with this, but that does not work on temperature. Guys will say, hey, Dave, my flame rod is glowing, and it keeps going out. It has nothing to do with it. That flame rod is completing a circuit. So there's a voltage coming out of the flame rod. The flame carries it to the ground, completes the circuit. That's how it proves the flame lit. Now, if we look above here, you'll see, do this. You'll see the flame rod is at one end, the sensor's at the other. All right, so the flame rod is at the far burner from the igniter. That means all four of these burners have to light to prove that there's flame. So that's all done on purpose. So if only two burners light, we're never going to get to the flame rod, so we're never going to prove flame, and we'll drop out. Okay. So, and now we've added a rollout limit. So what happens is if the flames start to roll out, we've got another limit that's going to shut this thing down. Okay, so here's another look at the burners removed, so you can get a better look here. And you can see right there is where the orange wires are, that's the igniter, the electrode. And then where the yellow wire goes, that's the sensor. So the flames would have to carry all the way across to that yellow wire sensor. And then we'd have to carry a voltage through the flame to ground. So we've proved all the burners lit. And now we send that signal back to the controller that says, yes, we have a flame. Go ahead and light. Now, then we get into the direct ignition. Okay, so this didn't use, an igniter or a hot surface igniter. This goes direct spark. Okay, so it's going to spark, it's going to ignite directly. So the electrode is going to directly light the main burner. All right, but either one, they work pretty much the same way. So what happens? So on a call, on almost every draft induced furnace, single stage, two stage, variable speed, pretty much works the same way. Nothing can happen until that inducer's running, right? Because we got no draft, right? We can't light anything until we create a draft to get proper air moving for proper combustion. So the thermostat turns the inducer on. Once the inducer comes on, it closes a pressure switch. Nothing can happen until that happens. So if you see a furnace sitting there with just the inducer running, we might not have closed the pressure switch for whatever reason. So pressure switch closes, that starts the ignition. So that tells the igniter, okay, inducer's running. We're going to send power to the igniter or the spark or whichever it is. So in this case, it's hot surface. The igniter is going to come on for a period of time, usually 3 to 6 seconds. We're going to send power to the valve, which is going to open the valve. If the burners ignite and the flame rod picks it up, remember, it carries all the way across. The flame rod senses it by carrying voltage through the flame to ground. It tells the module, burner's lit. As the furnace heats up, the fan control turns the blower on. All right. If we never prove flame, it'll lock out. Okay, so then we get into the modern furnace control board. So now we've combined everything, into one single control board. So operation is pretty much the same, but we've eliminated the ignition control. If you look up there, you see the fan limit control is gone. The fan control itself is gone, because everything's going to come from the main board now. So there's the main board. We've got 24 volts going through my limits. In this case, I got a rollout limit, a main limit, brings 24 volts to the board. Sits there ready. Thermostat. Hey, need heat. Inducer starts. So the board starts the inducer. What I say about the pressure switch? Nothing happens. Pressure switch tells the board, we got a draft inducer. The board starts the igniter, opens the gas valve, proves the flame. After a given amount of time, the blower starts. Okay. And if any time along the way, if we lose the flame or if one of those limits open, everything drops out. All right. And we restart. Okay. All right, so the modern 90% furnace sequence of operation. Now, this is pretty standard, regardless of which variety you're working on. Thermostat calls for heat, the inducer motor starts. First and foremost, makes a pressure switch or draft switch. Igniter warms up or the sparker starts, whichever begins. After a set amount of time, the valve opens. We have another set amount of time that it's going to allow the flame rod to prove the flame. If it doesn't, locks out. After flame has been established, after, again, a predetermined amount of time, between 30 and 90 seconds, the blower will come on. After the burner shuts off, on time again, the blower will shut off. Most cases, a limit trip now will turn the blower on. All right, so that's pretty standard on pretty much everything. Okay, so again, the draft switch on a modern 90% furnace. So the draft inducer's at the bottom. That's where that green And then the draft switch is hooked into the bottom there as well. And that's going to create a negative pressure because that's drawing on those heat exchangers. So the vent is positive, but the heat exchanger itself is a negative. So that switch has to close before anything else can happen. If that switch is closed before the process starts, it won't start. Okay, because it knows something's wrong. Now, why would the switch not close? Well, look at the vent. Do I have a plug vent? Do I have cracks in heat exchanger? Do I have plugged heat exchangers? Is that pressure switch bad? Okay. So which is which? Remember, they both have fans. Well, the telltale signs is the 80% are over there. The fan is metal. It's got metal vent pipe. All right. It's only 80%. The 90% has a plastic fan because it's going to get water in it, and it's at the bottom. Generally, the burners are on the top, the inducers at the bottom. Over there, you can see the burners at the bottom, the inducers on the top. Okay, 80% or 90%. All right. Configurations. Nowadays, most furnaces are convertible, but we're going to just talk a little bit about the configurations of standard furnace. So here we have a furnace in the upflow configuration. Thinking computers. All right. Blowers on the bottom. The return comes down to the side. We go through the blower up through the heat exchangers to the space. So here's a 90% furnace in the upflow configuration. You can see the return air is on the left. So the air is coming into the furnace return. The blower's in the bottom under the heat exchangers. You can blow the air through the heat exchangers into the ductwork. That is a 2-pipe 90%. And if you look off to the side there, you'll see this drain pipe right here. Right there. That's the condensate drain. Okay, this same furnace, and most furnaces nowadays are like this, we can also put it in the counterflow or downflow configuration. That's where we put the blower on the top, heat exchangers on the bottom. So now the return's coming into the top, the ductwork's down in the bottom like in a crawl space here. So if I look at this, up at the very top, oh, there you go. You see the return air coming in, you got an air cleaner up there, and then the blower, and then it goes through the heat exchangers, and then the ductwork discharges at the bottom. This 2 is a 2-pipe 90, so we're bringing fresh air in from outside. And then we have a horizontal furnace. Most furnaces now do all 3. So now the blower, the return's coming in from one side, goes into the blower, heat exchangers, your supply ductwork. Okay, so again, here's that same exact furnace laying on horizontal. You got your return on one side, your blower, your heat exchanger, and then your supply. Again, this one is piped in the 2-pipe configuration, so we're bringing outside air. Okay, so that's what I have. We are right at a little over 11:30, so one a little bit long. For basic heating, again, an idea to kind of get your guys' feet wet, get and understand combustion, basic controls. So that's what I have. So are there any questions, Isaac? I don't see any questions
Nope.
coming in.
No, nothing in the comments.
Okay. All right. Again, and if you think of a question later, feel free to reach out to me. Here's my email address right there. You can also just put Dave P at Behler or b-y.com. Oh, I put com twice. Anyways, you can reach out to me. If you think of a question later, feel free to reach out to me later. Email address right there, but com's only once. That's not twice. All right. So anything else?
I think we're all set. You all get a follow-up email from me regarding the class, and yeah, we should be all set, Dave.
All right, and he's gonna say, yeah. So you're gonna. Oh yeah, and I asked that when you get the critique for the class, please take a minute to fill it out, okay? Because we're still getting used to doing this online, virtual stuff. We're trying to make some changes. I think you can see some of them now with how we're doing our presentation. So input from you guys is going to be very helpful. So please feel free to reach out, or I ask that you reach out, fill out the critique, and so we can get the feedback, again, and that helps us to do a better job, with the presentation. So I really would appreciate if you take the time to do that. All right. So if
Awesome.
that's all.
Go ahead.
Oh, all right. Yeah. All right. Thanks, Isaac. Thanks, everybody. It's almost lunchtime. So
Yep.
that's
Yeah, thanks. Thanks so
All
much,
right.
Dave, and thanks everyone for getting online, and have a great rest of your day.
all right. You too. Thank you, everybody.